The P-51 Mustang, the most dominant escort fighter of World War II. It helped blaze a trail from England all the way to Berlin for America's bomber force.
Of course, the Mustang was a revelation. It was a war winner.
Its creation was sparked by a mixture of genius and chance. The Mustang and its two-stage, two-speed supercharged Merlin engine were the end result of years of technological development. From World War I to World War II, each generation of aircraft went ever higher and faster. But the Mustang's marriage with the Merlin might never have happened. National pride delayed the coupling of these two great innovations. But a new, deadly German adversary changed everything.
The Focke-Wulf 190, this was really a top-notch fighter aircraft.
With the FW-190 terrorizing the skies of Europe, the British and American forces swallowed their pride and joined together to create the ultimate fighting machine. December 17, 1903. The Wright brothers' aircraft, the Wright 1, successfully takes off, initiating the dawn of aviation. Man had already taken to the skies with gliders and balloons, but this was the first time that an engine had propelled him into the air. The Wright 1's engine was a crude design by today's standards and put out 12 horsepower only. It was an inline engine, meaning that its cylinders, 4 in total, were mounted in a straight line, a layout that would inspire some of the most advanced piston-engined aircraft ever created. Though a simple design, the Wright engine was innovative. It was the first engine to make use of a lightweight cast aluminum crankcase. Every pound counted. With a heavier engine, the Wrights may not have made history that winter's day in North Carolina. Aircraft weight and power would continue to be important to the evolution of flight. World War I was approaching, and the newly formed air forces of the world needed reliable engines with enough power to sustain flight during operations. From France would come a new type of power plant to take the fight into the air, the rotary engine. Rotary engines operated differently than the inline ones used by the Wright brothers. The cylinders were arranged in a radial pattern rather than a line. When the engine was fired up, the crankshaft remained stationary, while the crankcase and cylinders rotated around it. A rotary engine had one giant advantage over the inlines of the era. It was much lighter, and thus gave a pilot better performance during combat or while trying to evade an enemy. However, the rotary engine was not without its shortcomings. It had poor fuel economy, as it was often run on full throttle. It also provided an unpleasant ride. Castor oil was mixed with the fuel mixture for lubrication, with the side effect of heavy fumes, smoke, and an oil shower for pilots. Turns with a rotary-powered aircraft could prove treacherous. As the whole engine rotated, it produced a gyroscopic effect. A turn to the right, at full power and low level, could end with the death of a pilot. Rotary-powered aircraft remained part of Air Force inventories till war's end, but they were gradually supplanted by the inline engine. Inlines, based on the same principles as the one found in the original Wright plane, kept improving in terms of power and performance. Between the wars and across the Atlantic, a new type of aircraft engine would emerge to dominate American aviation. The U.S. Navy was looking for aircraft to populate its fledgling aircraft carriers. Space on board was extremely limited, but aircraft with inline engines often had lengthy noses. Their engines, built with rows of cylinders, took up too much space on cramped carriers. Rotary engines, though more compact, had too many other weaknesses to be serious contenders for the role. There was, however, a third type of engine. Before the war, there had been limited experimentation with radial engines. At first glance, these appeared to be just like rotary engines, It's only when they are fired up that the difference becomes clear. In a rotary engine, the crankcase and cylinders rotate around the crankshaft. But with a radial engine, the crankshaft rotates while the engine block is static. Radials often weren't as powerful as inline engines, but they were less complicated. They were cooled by air rushing over the engine rather than through a liquid cooling system. This made radials less vulnerable to battle damage, which might rupture the coolant lines. Navy pilots who might have to travel long distances over the ocean to get to a target needed an engine that would be sure to get them home under any circumstance. Most importantly for the Navy, radials were smaller than inline engines, so a greater number of aircraft equipped with them could be stored on board their carriers. The Wright Aeronautical Corporation, a successor to the original Wright Brothers Company, used their aviation expertise to create the first reliable radial engine for the Navy, the J-5 Whirlwind. The J-5 was put on display for the entire world to see when Charles Lindbergh crossed the Atlantic in his Spirit of St. Louis in 1927. His flight solidified the reputation of the J-5 Radial as a dependable power plant. The budding airlines of the world were looking for engines to power their airliners and to bring their passengers across continents and eventually across the globe safely. Reliable radial engines seemed to be the ideal choice. Radials would power many of the principal airliners in the history of civil aviation, from the Ford Trimotor to the Boeing 247 to the Lockheed Model 10 Electra. Both the U.S. Navy and U.S. Army Air Corps would rely heavily on radial engines as they built up their inventories of fighters and other aircraft. In the 1930s, the U.S. had just one inline engine in development, the Allison V-1710, an engine that would one day power some of America's great fighters. At the time, relying on radials seemed a prudent decision, but in the years to come and in the battles ahead, it will leave the U.S. playing catch-up with their allies and enemies in Europe. In Europe in the 1930s, air forces and aircraft manufacturers were looking for speed above all else as they designed the next generation of fighters. Using streamlined designs and powerful V-12 inline engines, they pushed their aircraft to speeds over 350 miles per hour. Their inline engines were not only more powerful, they also helped to create more aerodynamic airframes. Their elongated shapes allowed for more streamlined designs as compared with radials. Inline engines may have been more vulnerable to attack due to their complex liquid cooling systems, but no matter how durable a radial engine is, speed kills in a dogfight. Inline engines were built to provide just that. It was from this European obsession with speed that some of the legendary fighters of World War II were born, including the Supermarine Spitfire, the Hawker Hurricane, and the Messerschmitt Bf 109. Beneath their elegant frames purred ever more powerful inline engines from Rolls Royce and Daimler-Benz respectively. In the middle of 1940, the pilots of the RAF tested their mettle and the endurance of their fighting machines in some of the most spectacular air battles of World War II. Vice Fuhrer Göring had promised to destroy the RAF and thus facilitate the invasion of Britain. Göring had at his disposal an armada of medium bombers protected by a deadly fighter force. The result of the Battle of Britain during those few vital months of 1940 is well known. There was a heavy toll in fighters and pilots on both sides. British and German engineers tried to squeeze every ounce of power from their engines. Any tiny advantage could be the difference between life and death. With Britain and her industry under direct attack, she looked to her old colony more than ever to provide her with desperately needed aircraft. Even before the Battle of Britain, the British Purchasing Commission had already been shopping for additional aircraft. The US's initial offer of fighters was not well suited for the high-altitude dogfights taking place over Europe. This was partially due to the American engines available. The US had concentrated on radial engine production instead of inline engines like the ones so popular in European fighters. They did have the Allison engine, the V1710. Like the British Rolls Royce Merlin, it was a 12-cylinder inline engine, but it had a complex turbocharger often difficult to fit into an aircraft. To boost power in the thin air at high altitudes, the Allison engine used the heat of its exhaust to power a turbine and thereby increase the airflow and power. One American aircraft, the Lockheed P-38, had the extra space needed to house the turbocharger. It was a big twin-engined aircraft to begin with and had space in its tail booms for the extra equipment. But given the size of the P-38, it wouldn't have fared well against nimble single-engine German fighters in a dogfight. America had other smaller fighters powered by the Allison engine, the P-39 Airacobra and the Curtiss P-40 Warhawk. In both cases, their manufacturers failed to include Allison's turbocharger. The P-39 had an innovative layout, with its engine situated mid-fuselage, behind the pilot. It was designed to house both the Allison engine and the turbocharger. However, a scoop built into the left side of the fuselage to cool the turbocharger was deemed too aerodynamically expensive. Both the scoop and the turbocharger were eliminated from the production design. This change crippled the Aerocobra's ability to fight at high altitudes. In the case of the P-40 Warhawk, a rugged, single-engine airplane, the turbocharger was excluded from the design from the get-go. This limited its optimal altitude to just 15,000 feet, and thus relegated the aircraft to ground attack work. The British Purchasing Commission was still interested in the Warhawk, even with its limitations. They saw it as more of an Army support aircraft. However, the Curtiss factory was running at capacity and could not fulfill the order. With no suitable aircraft readily available for purchase, the Brits would turn to North American aircraft. The British Purchasing Commission proposed that North American build the Warhawk under license from Curtiss. But NAA President Dutch Kindleberger had a bolder plan. He guaranteed that he could create an even better airplane, using the same Allison engine, in less time than it would take for him to retool for Warhawk production. The Brits said yes, and the end result was an airplane that may well have changed the outcome of the Second World War in Europe. Back in Europe, Germany was looking for an aircraft to augment the Bf-109. In the Battle of Britain, the Bf-109 and Spitfire were closely matched. But the Bf-109 lacked the range to be highly effective in its escort role over Britain in the summer of 1940. The Luftwaffe had a twin-engined escort, the Bf-110. It had the range to be an excellent escort, but it lacked the maneuverability to defend itself or its charge in a dogfight. It also used two Daimler-Benz 605 engines, making it an expensive sitting duck for British interceptors. Looking for a quick solution to their escort dilemma, the Luftwaffe even considered having the 110s tow 109s into battle to conserve fuel. But in the long run, using two aircraft to perform the role of a single fighter was an even more wasteful solution. What the Luftwaffe needed was a dedicated single-engine aircraft to fill in for the Bf-109 on longer-range missions, and ideally something to give them a decided advantage over the British fighters of the time. However, the Luftwaffe wanted to have its cake and eat it too. They wanted a new fighter, but they didn't want to sacrifice any of the precious 605 engines meant for the Bf-109. To the consternation of the Luftwaffe, most of the new submissions for fighter designs from German industry were to be built around this very same engine. To solve Germany's escort woes, one man, Kurt Tank, Focke-Wulf's legendary designer and test pilot, did what was almost unthinkable at the time. Since the start of the war, British and German designers had relied upon powerful 12-cylinder inline engines to power their fighters. Tank dared to build Germany's next fighter around a bomber's radial engine. The air-cooled BMW 801 radial engine had plenty of power and had proven reliable in the Ju-88 and Do-217. But radials in a fighter were a rare sight in Europe. It was difficult to build this aerodynamic a fuselage to house them in, as when constructing one for a slender inline engine. Though an unconventional design track, Tank saw two reasons for encouragement. Firstly, the National Advisory Committee for Aeronautics in the U.S. had already done research on improving airflow around radial engines. Over time, they had developed the NACA cowl, which at least helped to reduce drag. This was a simple ring which fitted snugly around the cylinders of a radial engine. It not only made the engine more aerodynamic, it also improved cooling. Secondly, Tank observed that the US and Japanese navies were employing several modern carrier aircraft, all with radial engines. Aircraft like the F-4F Hellcat and the Japanese A-6M-0. The lightweight Zero had been almost unstoppable in the early part of the Pacific War. Tank had continued to explore ways of improving his new radial-engined aircraft and reducing the drag effect, although some say his greatest task was selling the radial idea to the ministry. If that was the case, the bureaucrats must have been quickly won over by Kurt Tank's first prototypes. Given the designation the Focke-Wulf 190, and unofficially known as the Butcher Bird, the Luftwaffe's latest fighter was rushed into production. Fortunately for the Allies, the FW-190 arrived after the close of the Battle of Britain. In the summer of 1941, 5 Mark V Spitfires flying over the south coast spotted several radial engine fighters in German markings. At first glance, they were mistaken for US-built Republic Lancers. It was a deadly case of mistaken identity. The aircraft were, in reality, early model FW-190s. The Spitfire pilots who survived the ensuing battle lived to tell just how quickly their comrades had been lost. But Britain's greatest loss that day was not pilots or planes. The battle marked the day Britain lost air superiority to the Luftwaffe. The RAF had to do something, and fast. All eyes looked to Rolls Royce, manufacturer of the Merlin engine, the power plant of the Spitfire, Hurricane, and so many of Britain's great planes. Although the company had the next-generation engine, the 12-cylinder Griffin, in development, it was well over a year away, more than enough time for Britain to lose the war. Earlier, there had been some thought given to modifying a few Merlin engines for experimental high-altitude work to be executed by a Wellington bomber. It was little more than an idea at the time, but in Britain's hour of desperate need, Rolls-Royce engineers worked night and day to test the concept. Merlin engines were already supercharged. An air compressor mechanically attached to the rotating camshaft increased the airflow to the engine, allowing it to burn more fuel and to boost performance. Rolls-Royce engineers had theorized that adding a second supercharger could give the engine even more punch during high-altitude work. Might a two-stage supercharger help the RAF reclaim air supremacy? The end result of the Rolls-Royce experiments was breathtaking. It was almost as if the two-stage, two-speed Merlin was an entirely different engine, when in fact it was just a modification. When the double supercharged aircraft, dubbed the Spitfire Mark IX, finally arrived in June of 1942, the RAF had a rare opportunity to test it directly against a captured FW-190. The test results were far different than the day a group of unlucky RAF pilots ran into a flock of butcherbirds. The two aircraft were virtual equals in terms of performance. Captain Eric Brown, who had flown a captured FW-190, had a chance to test the new Spitfire 9 against the German aircraft in live combat.
I'd flown the 190 quite a bit, so I wasn't too frightened. I reckoned I knew what that aircraft could do, and I knew what my Spit could do, so I thought, well, I can handle this guy. Hoping he was somebody just out of training school. But no, I picked somebody who really knew what he was up to. And we had, I would say, a toing and froing over France. But neither could get a draw bead in the other. We finally realized, as both of us, we run out of fuel. We waggled our wings at each other and departed. And I realized this was really a top-notch fighter aircraft.
The RAF had leveled the playing field with the Luftwaffe, at least for the time being. But what the RAF really needed was an aircraft to give them the upper hand. The new Merlin's greatest contribution to the war was still to come, when it was mated with an extraordinary aircraft of American design. Back in the U.S., North American Aircraft had continued to work on a Warhawk substitute, which met the specifications laid out by the British Purchasing Commission. They had specified that the airplane be powered by an Allison engine, that it cost less than $40,000, and that it be armed with 4 .303-inch machine guns. North American answered with the P-51 Mustang. It featured an advanced laminar flow wing for good aerodynamic efficiency, and a wide gate undercarriage for safer landing. Pleasing to the eye and to fly, although mainly at lower altitudes, the new arrival quickly gained respect from pilots and ground crews alike. There were some concerns about how the Mustang would fare should it be forced to ditch while crossing the channel. During a water landing, its air scoop, located beneath the fuselage, might flood the aircraft or cause it to overturn. Water tank tests at Saunders Row were initiated to perfect the techniques for ditching the aircraft. Around the same time that the RAF was getting the Spitfire Mark 9 ready for combat, and the FW-190 was dominating the skies, Rolls Royce test pilot Ronald Hawker was tasked with the mission of evaluating all aircraft powered by non-Rolls Royce engines. He was thoroughly impressed with the P-51A, save for its poor performance at high altitude. Like the P-40 Warhawk, it had an Allison engine and no turbocharger. Hawker pondered how the aircraft might perform with the new Merlin engine. The results on paper were phenomenal. According to Rolls-Royce's calculations, with a Merlin power plant, the Mustang would not only outclass any American aircraft, but even new Spitfires using the same engine. Oddly, Hawker had to push for the mating of the Merlin 61 and the Mustang, even though the double supercharged P-51 would have outclassed the FW-190 as well. Hawker finally arranged for the marriage of the two great inventions, and test trials confirmed his hunch. The Mustang was a war winner. The main challenge was to produce enough aircraft and engines to reclaim the skies of Europe. North American would tweak the Mustang design to accommodate the Merlin 61 engine. It was a much more powerful engine, so the original P-51A airframe had to be reinforced. As well, the three-bladed prop was exchanged for one with four blades. The addition of plumbing for drop tanks might have seemed a small change, but it would have a great impact on the air battles to come. Packard took up manufacture of the Merlin 61 engines in the U.S. They were designated the V1650s. Packard had arranged a licensing agreement with Rolls-Royce earlier in the war. Ford was originally slated to build American-made Merlins and seemed a perfect choice due to the company's industrial might. But Henry Ford was adamant that his company build defensive weapons only. North American's double supercharged aircraft, the P-51B and P-51C, first took flight in the spring and summer of 1943. Air Vice Marshal Patty Harbison recalls when the Mustangs first arrived at his Spitfire squadron.
Well, of course, the Mustang was a revelation. It was a much more comfortable airplane than the Spitfire was. And I have heard people talk about the relative merits of both. They were both war winners. The Spitfire was built as an interceptor. It could outturn a Mustang and it could outclimb it, but it didn't have the legs the Mustang had. And of course, if you can't get to where the fight is, you're not too effective.
As P-51 started to arrive in Europe, the war was changing, and the Mustang was the perfect aircraft for the time. The U.S. was taking the war to Germany. They were bombing the German war industry out of business. The only problem was their bombers were being shredded by speedy German interceptors. The U.S. had hinged their hopes on the ability of their bombers to defend themselves by maintaining a tight box formation. When this strategy failed, they were in dire need of an escort fighter. The P-38 Lightning was simply not agile enough to take on the role. Then there was the P-47 Thunderbolt. It was an awesome radial engine fighter, more than capable of taking care of itself in battle. But it had two major flaws. It was expensive, and it lacked the range to take the bombers all the way to Berlin and back. The P-51 Bs and Cs arrived just in time. They had been designed to carry drop tanks, and with the addition of a fuel tank behind the pilots, they had more than enough fuel to escort American bombers to Hitler's lair. The Mustang proved more than a match for Germany's FW-190 and Me-109. Slowly, American bombers closed in around Berlin. Suddenly, the Germans found themselves playing catch-up. Kurt Tank's FW-190 with a radial engine found it difficult at higher altitudes where the bombers roamed. Tank swapped its radial engine for an inline. The long-nosed aircraft was nicknamed the Dora.
The Focke-Wulf Dora, the later Dora, was a magnificent fighter with an engine change, not really any structural changes other than those to accommodate the engine. But what it meant was, here was an airplane that could keep up with the hunt as the years of the war progressed. So from 1942 right up to the end of the war, the Focke-Wulf 190 was in the top grade of fighter or fighter bomber.
The P-51 Mustang also continued to evolve as mechanics and engineers incorporated changes based on the feedback of pilots who had tested the plane in battle. Its canopy went through several permutations. The British swapped the original one for a sliding Malcolm hood, similar to a Spitfire's for improved visibility. The P-51D, the definitive version of the Mustang, had a bubble canopy, which offered 360 degrees of clear view. North American also upgraded the D's firepower. It had 650 caliber machine guns compared to 4 in earlier models, and it had solved the problem of gun jamming during hard turns. The fuel tank situated behind the pilot may have increased range, but it created other issues. The plane had poor directional stability when the tank was full. To counter this problem, engineers added a small dorsal fin in the D model. These and other improvements would help the Mustang blaze a path to Berlin for America's bombers. Reichsmarschall Hermann Göring, commander of the Luftwaffe, was quoted as saying, "When I saw Mustangs over Berlin, I knew the jig was up." When the European war had come to a close, the battle still raged in the Pacific. The Mustang was the best escort available, but even with its incredible range, it could not accompany an aircraft like the B-29 Superfortress on extended bombing missions over Japan. The expanses of ocean were too large. The engineers at North American struggled with the problem of stretching the Mustang's range. Their solution was a Zwilling or twin Mustang. By fusing two Mustangs together, they hoped to dramatically increase the range of the Mustang while retaining its excellent dogfighting abilities. The new Mustang, the F-82, had an incredible range, 2,000 miles. Though the prototypes were powered by Packard-built Merlin engines, the U.S. Army Air Corps was adamant that the production version be totally American-made. Unfortunately for the F-82, without Merlin engines, it was not the same aircraft. When fitted with the Allison V-1710-100, its speed dropped and high-altitude performance suffered. It was one of the few cases of a prototype outperforming the production model of an aircraft. By the time the F-82 was ready, Japan had surrendered, and the war was over. After the war, the P-51 continued to serve, while other piston engine fighters of the era went quietly into retirement. Though it was the dawn of the jet age, there was still a place for the Mustang in a variety of roles. Colonel Ray O. Roberts flew the Mustang during its second life.
At that time I was flying what they call the F6, which is a P-51 with cameras. Also had guns, and you could have the bombing and gunnery capability. And we participated in a post-hostilities mapping program. We mapped, revised all the Japanese maps, photographed, did aerial photography in Japan and Korea.
When the Korean War arrived, Mustangs which had been mothballed for long-term storage were suddenly being shipped across the Pacific on carriers. Unable to compete with the next generation of jet fighters for the dogfighter role, Mustangs returned to where they started. In Korea, Mustangs made excellent ground attack aircraft. They didn't have the speed of jets, but they had the endurance to make it from Japan to Korea on bombing runs. In Korea, the F-82 also had an opportunity to taste combat for the first time. F-82s flew strike, escort, and night fighter missions. The marriage of the P-51 Mustang and the Merlin 61 engine produced incredible results. It provided the Allies with an effective escort to pound the last nails into Germany's coffin. Perhaps the most amazing thing about the P-51's stellar career is that it might never have happened. If the Merlin and Mustang had never been mated at the suggestion of Hawker at Rolls Royce, the P-51 might have had a humdrum career as a reliable ground attack aircraft, rather than an elite dogfighter. It arrived at the right time and the right place in history, just when the Allies needed an escort fighter. The P-51 was the end result of years of aircraft and engine development. Though jet-powered aircraft would supplant it, the impact of the Mustang and Merlin in military history cannot be unwritten or denied.
When in 1938 war clouds were gathering over the continent of Europe, the Rolls Royce factory in Derby assumed a new importance. Home of the company since its inception in 1906, it was from here that one of the United Nations' greatest contributions to victory was brought to fruition by a picked group of designers, engineers and executives under the able leadership of Sir Arthur Sitgreaves and Mr. E.W. Hyves. Inspired by the tradition handed down by the late Sir Henry Royce that only perfection was good enough, management and workers set about the task of further developing an aero engine which would enable the air forces of democracy to sweep the enemy from the skies and bomb his industries into submission. This engine was the Merlin. Away from imminent danger of air attack, an unobtrusive country house set deep in the Derbyshire countryside sheltered the Rolls-Royce Aero Planning Department. Here, engine designers worked under conditions of highest secrecy on the development of the Merlin engine, armed with data and experience gained from previous engines. The main characteristics of the new engine had already been decided in theory by the Engine Development Committee at Derby, and now began the task of calculating main dimensions and producing the plans for quantity production. At the same time, scale models of complete engines and power plants were made of wood in order to visualize and check the exterior dimensions, while much time could be saved in checking the dimensional suitability of modifications. Matters like frontal area, engine weight, working of retractable undercarriage, position of center of gravity could all be deduced from measurements and behaviors of these models. Next step was the making by skilled engineer draftsmen of many thousands of detailed working drawings, which would constitute the basis for building the prototype. As these drawings had in turn to be duplicated for use in the workshops, a blueprint department with an average output of 6,000 drawings a day was brought into being. At the experimental shop in Derby, emphasis is on the man rather than on the tool. Versatility is the keynote. Every job is different, and the men in this shop are among the most skilled workers in the Rolls Royce organization. Soon the first components begin to take shape. In the experimental shop, the tool equipment is less specialized than that of the factories on production work, as it is concerned mainly with one-off jobs. Where duplication is necessary for parts like connecting rods, a Keller machine is used. The cutters are made to follow a master template, producing several identical pieces at a time. Few jigs and fixtures are available in the experimental stage, so the alignment of a machined surface is checked on the marking-off table. A new engine is seldom built complete at first, so that although the production engine may have 12 or 24 cylinders, the first experimental job may only consist of one section of the crankshaft. And from this single-cylinder engine comes the first positive information. From these results, a forecast of the behavior of the full-size prototype can be made. When the prototype is assembled, it goes to the test house. The engine is coupled to a dynamometer, which is a form of water brake, which absorbs the entire power output of the engine, and is capable of adjustment so that the characteristics of the engine at different loads and speeds can be measured. The control panel also has instrument consumption, boost pressure, oil pressure, coolant temperature, engine revs, power output, and many other quantities. Ever since it was first developed, the rated horsepower of the Merlin has steadily increased. The later types have a power output 2 or 3 times as great as that of the original prototype, without any great change in leading dimensions. After test, the prototype is stripped down, and its parts are subjected to minute inspection. Parts which show signs of undue stress or wear are examined by the chief engineer and designers, who decide what alterations in design, manufacturing methods, or materials are necessary. Once the prototype has passed its first test bed trials, it undergoes further tests with the air screw fitted. Finally, it is ready for its flight test. Installed in an aircraft fuselage, the Rolls-Royce test pilot takes off to confirm that the Merlin engine will in practice do as much and even more than the designers had planned. Realizing that quantity, as well as quality, would be the need of the day, the Air Ministry asked Rolls-Royce to build a large factory away from Derby for the quantity production of Merlin engines. In 1938, work began on the erection of a large ultra-modern plant at Crewe, while in 1939, as war became a certainty, the company were asked to build yet another factory about twice the size of Crewe. Glasgow was selected, and work commenced on the Glasgow plant in July 1939. By early December, the first machine tools were already in production on the Merlin. In laying out the various factories for quantity production, the problem of the most efficient placing of machines and processes was solved by making planned silhouettes to scale of each machine and item of workshop furniture. These silhouettes were then maneuvered on a scale floor plan until the ideal disposition was found. The layout was then photographed, and copies were sent to the plant engineers. As soon as all the machines were installed, full-scale production on Merlin engines commenced. Producing the Merlin engine in vast quantities without losing anything of the world-renowned Rolls-Royce qualities of precision workmanship presented untold obstacles. Apart from the difficulties of operating under wartime blackout conditions and the demands of the fighting services on road and rail transport, making difficult the movement of raw materials, there was the problem of labor. To overcome the manpower difficulty, training establishments were set up in various parts of the country. Under the tutelage of skilled Rolls Royce craftsmen, both men and women were given intensive training in the operation of highly specialized machine tools in a section of the factory specially equipped for this purpose. In order to increase the supply of engineering draftsmen, experiments were made in training women of suitable educational qualifications. Inspired by the firm's tradition, these women eagerly proved their aptitude for this exacting work, and large numbers graduated to works drawing offices at the various plants. Apart from training men and women for aero engine production, the company was faced with the problem of housing and transporting them to and from work. At both Crewe and Glasgow, housing estates and hostels were built within sight of the plant to shelter the workers who had come from all over the United Kingdom. In view of the fact that in Glasgow alone over 1,500 houses had been built, the local transport companies were called upon to cooperate in organising 126 special bus services to and from a depot inside the works itself, enabling the workers to get immediate transport to outlying districts. To protect the factories against air and ground attack, strong Home Guard and civil defence detachments were formed, made up of volunteer workers from the various plants. Fire brigades, also manned by workers, soon reached a high degree of proficiency and were equipped with motor pumps and all the latest firefighting appliances. The Rolls-Royce organisation was possibly unique in having its own bomb disposal unit, equally prepared to play a vital and dangerous part in an emergency. In order to safeguard the workers' health, an efficient medical organisation was brought into being. All new workers were given a medical examination and eyesight test, while surgeries and restrooms, staffed by resident doctors and nurses, were a feature of each plant. In order to ensure maximum cooperation between workers and management, joint production committees were formed at each factory, consisting of representatives of the management and representatives and shop stewards of the workers. Vast stocks of raw materials were built up, and a sample of every piece of incoming bar, tube, rod, or forging was sent to the laboratories for analysis. Each batch of material was given a number which stayed with it through every process, and a sample was taken so that a fault developing at any time during the component's history could be traced back to the raw material stage. Some of the most valuable raw materials were the light metal and other alloys discovered and developed in the company's research laboratories at Derby. Apart from the famous RR-50, used in the manufacture of castings, many other equally important contributions to the Allied war effort were made by the pick of scientists and technologists working in these laboratories. In the Rolls-Royce drop forge shop, alloy steel forgings were pounded out night and day. The most highly stressed components of the Merlin engine are made from these forgings, which allow a very high output of accurately formed parts, while the metal itself, due to its molecular flow under the blows of the forge, becomes more homogeneous and capable of withstanding higher strains. In the manufacture of the Merlin engine, the light alloy foundry at Glasgow is unique in the Rolls-Royce organisation and probably in the world. The foundry, with its core, moulding and fettling shops, occupies 2 entire blocks of the factory and is organised, like the rest of the plant, on a flow production basis. The layout of the foundry and its organisation for production constitute a great feat of technical planning. Every kind of casting used in making Merlin engines is produced here. Very many difficulties had to be overcome on the material side of the process, and the achievement is made more remarkable by the fact that many of the workers are trainees, a large proportion of them women. Core making is a process which illustrates the way in which complex operations normally requiring much time and a high order of skill have been rendered rapid and certain in the hands of trainees of both sexes. The lighter cores are made by hand and mainly by women, on core tables to which ready-mixed sand is delivered by an overhead conveyor system. All the 300-odd intricate cores which go to each engine are made in the same manner. Organisation has made each individual job simple. Men make the heavier cores by machine. A number of heavy cores are used in the upper half of the crankcase mould to form the bearing webs, This is one of the two main moulding bays, which are arranged on either side of the line of furnaces. The moulding machines are mostly of the rollover jolt type, both hydraulically and pneumatically operated and very simple to control. This mould, for the upper half of the crankcase, is the largest on the engine. Complete with cores and moulding box, it weighs a ton. The number of cores in the mould are an indication of the intricacy of the casting. This mould of the upper half crankcase, although the largest, is by no means the most intricate in the engine. The aluminium alloy, principally the famous RR50, is melted in gas-heated tilting furnaces, adjacent to the mould conveyors. The larger moulds are poured from two sides simultaneously. This allows the use of ladles of manageable size and also tends towards an even temperature of metal throughout the mould. Very many and very large risers are employed to ensure sound metal in the casting. Castings are fettled in this bay with power saws and pneumatic hand tools. The first job is cutting off the runners and risers. On large castings, these are very massive, and a special type of twin-hand circular saw has been developed to do the job. The saws cut into the surplus metal from both sides so that it can be easily broken away at the end of the cut. Final fettling of the castings is done with pneumatic chisels. These cut away all the flash and webs which are not needed in the finished casting. Every casting is inspected before it goes for heat treatment. Before the castings are machined, they undergo heat treatment in this 88 feet long priest furnace. The castings are loaded onto bogies, which are pushed into the front end of the furnace. This automatically pushes out a completely heat-treated load at the other end. It has 3 heat zones, and the temperatures are automatically regulated within plus or minus 2 degrees centigrade. Very many Merlin castings are produced by die casting. Metal moulds, or dies, are used in this process, which thus effects a considerable saving of time, since the same mould can be used over and over again. The die castings are taken away on the conveyor for heat treatment in the same way as sand mould castings. These die castings can be made to much finer limits than can ordinary sand castings. The surface is smoother, and because no gases are evolved in the mould, the metal is usually more homogeneous. The castings go to the machine shops for finishing. During the last few decades, amazing progress has taken place in the development of very elaborate and complex machine tools, both automatic and semi-automatic. Even in the hands of trainees or unskilled operators, these machines can and do perform the apparent miracle of producing in vast quantities the most intricate parts with the highest degree of precision. Actually, many men and women classed as unskilled or semi-skilled have become highly skilled and proficient in working a particular machine or operation, but the term is still used to distinguish them from the fully skilled Rolls Royce operator. Operators, such as those at the Derby Works, have served a long term of apprenticeship, and schooled in the Rolls Royce tradition have become qualified by this skill and experience to set up any machine and make the many adjustments necessary to keep it producing accurate work in the hands of trainee operators. Many of these machines have actually been developed by Rolls Royce engineers, and such is the final simplicity of operation that although a skilled man would need vast quantities of complex drawings to make the parts by hand, these company-developed machines can be handled by comparatively inexperienced trainees, while still retaining the rigid Rolls-Royce standards of precision. The crankshaft is probably the most highly stressed component of an aero engine. Over 140 separate machining operations are needed to produce the Merlin crankshaft. For these processes, a large number of special-purpose machines were developed by Rolls-Royce, including vertical and horizontal automatic lathes, deep drilling and grinding machines, and these crankshaft lapping machines. The rough crankshaft forging weighs 250 pounds. In its finished condition, the shaft weighs 108 pounds. The connecting rod is another highly stressed component of the engine, and over 160 operations are necessary to produce a completely articulated pair. After every machine operation on a Rolls-Royce component, the part is subjected to careful inspection before passing on to the next operation. Women prove themselves to be particularly adept at this exacting work. There are over 11,000 parts in a Merlin engine, and a high proportion of the smaller items are made from bar material on automatic and capstan lathes. Except for tool setting, this work is repetitive, though quite an amount of skill is needed to be a good operator. Nevertheless, the consistently high output figures on close limit work to Rolls Royce standards, achieved by trainee men and women who previously had no experience in the engineering industry, is indeed a remarkable achievement. Some 90 different types and sizes of gear wheels go into the Merlin, and all must be produced to exceptionally high standards of accuracy. Accurate tooth form and perfect structure of the metal itself is vital to the smooth running of gearing. A special gear analyzer is used for measuring the tooth forms of helical gears. This apparatus traces an enlarged graph, showing any departure from the theoretically perfect form. Great care and thought were devoted to the development of valves and valve springs. Machined from forgings, the first valve forming operations are done on turret lathes and automatics. The heads and seating faces are covered with a special heat-resisting nickel-chrome alloy, applied in the flame of an oxyacetylene glow lamp. Exhaust valves are made with hollow stems and are half filled with sodium, which melts at a low temperature. When the engine is running, heat is transferred from the head of the valve to the stem by the sodium splashing up and down. Valve springs are made from coils of high-tensile steel wire, in a specially designed machine which coils valve springs continuously and automatically cuts them to length. After grinding and finishing, the springs are tempered in a special furnace. The journal and big ends of the Merlin run in bearings of a lead-bronze alloy. The bearing shells are made of steel, into which are inserted casting tubes, secured by spinning their lower edges over in a lathe. After the shells have been preheated, the lead-bronze alloy is cast from a parametrically controlled electric induction furnace. The poured liners are then placed in a special cooling device, consisting of a cylinder with jets of water spraying inwards. The rotor of the supercharger is outstanding among the light alloy components of the engine. This component may be called upon to run at between 20,000 and 30,000 revolutions per minute, corresponding to a peripheral speed exceeding the velocity of sound. It is, therefore, in the highest degree important that this rotor should be perfectly balanced. This is achieved by machining it all over. There are countless machining and finishing operations involved in the manufacture of thousands of other Merlin engine components. To each of these, unstinting thought and care were given in devising machines and machine tools capable of producing the required rate of quantity output without losing anything of the traditional Rolls-Royce quality. In order to ensure that the standards of manufacture were being maintained, Rolls-Royce engineers developed many high-precision measuring gauges and other complicated items of inspection apparatus to augment and improve the standards of normal engineering precision gauges. Inspection of each of the 11,000 Merlin components, not once but many times, was continuous throughout every stage of manufacture, including a thorough final inspection when the parts were completed. Every factory has at least one air-conditioned, temperature-controlled standards room, in which the gauges and inspection devices used in the manufacture of Rolls-Royce engines are continually checked against standard gauges and precision comparators, whose accuracy is of the order of 10/millionths of an inch. When the finished components reach the sub-assembly stage, the engine begins to take shape. The assembly process is arranged as a sequence of operations in the same way as the machining. The sub-assembly benches are arranged in lines between the finished part stores and the engine erection lines. The component travels along the assembly line through the hands of dozens of different workers who each add their part or do their particular operation so that the component is finished at the end of the line. Components like the supercharger are built up separately, so that they go into the engine as complete units. At the end of the subassembly lines is the engine assembly shop, where the subassemblies are delivered at convenient points and are put together to make complete engines. Engine assembly starts with the crankcase, which has had all its studs and cylinder holding down bolts fitted on the subassembly benches. The engine assembly line has a bench-height rail track down the centre, which enables the work to be pushed easily from station to station along the line. A turntable in the track at each siding enables the engine to be run off the main line while fitting is in progress, leaving the main line free for the flow of work. At each station, a subassembly or component is added to the engine. As the engine passes down the line, it gradually takes form. The policy of specialization is applied here in the same way as in the other departments of manufacture. Each job is done by a crew who are specialists in fitting their particular component. This policy enables the workers to become expert in a short time. At the end of the line, the completed engine is vetted by an inspector who notes the numbers of individual components and assigns a new number to the whole engine. From now on, it has an identity. It is given a logbook in which all its subsequent history will be recorded, but meanwhile it is to be taken away for its first run on the test bed. Every Merlin is run on the test bed before it is passed into service. The Ministry of Aircraft Production prescribe very stringent tests for engines to be used in the RAF or the Fleet Air Arm, so several hours' run at the rated horsepower of the engine are followed by bursts at maximum power, while test engineers make careful notes of the engine's behavior. A certain proportion of engines which have satisfactorily passed their tests are nevertheless brought back and immediately stripped down. The running test demonstrates that every component is capable of doing its job. This strip down is to make sure that there has been no overheating or overloading, and to ensure, in short, that the engine will go on doing its job and maintain the standard of manufacture. Once more reassembled, the engines are ready for active service, but the job is not yet finished. Just before the war, it became apparent that in order to ensure the satisfactory installation of the engine and the consequent safety of the aeroplane's crew, it was necessary for Rolls-Royce to devote their engineering skill to designing the completely cowled power plant installation, ready for attachment to the aeroplane fuselage. This enterprise in tackling the complete power plant and developing it into a quickly detachable and interchangeable unit was acclaimed as one of the outstanding achievements of British aviation during the war. No survey of Rolls-Royce wartime service would be complete without reference to some of their many other contributions to the success of the Allied nations. Early in the war, it became obvious that the facilities which had been envisaged for the repair of damaged engines were going to prove entirely inadequate, and measures to remedy the position became of the utmost urgency. Rolls-Royce set about tackling this problem and had the satisfaction of seeing the figure of overhauled engines, which stood at a few hundred in 1939, rise to over 18,000 during 1944. The Rolls-Royce School of Instruction at Derby had trained nearly 17,000 people in the use and maintenance of Rolls-Royce engines and other products. Those trained included pilots, flight engineers, and ground personnel of not only the Royal Air Force and the Fleet Air Arm, but of representatives of the air forces of most of our allies. Another interesting example of Rolls-Royce versatility was the development of a small-caliber 40mm quick-firing gun for use in MTBs and similar craft. The Merlin engine was also adapted for powering these high-speed motorboats. Then again, there was developed a modified and unsupercharged version of the Merlin known as the Meteor, which was used to power the first prototype of a new tank. The effect of the extra power of the engine on the prototype tank was such that Rolls-Royce engineers were asked to collaborate in developing the tank itself. The fruits of this collaboration resulted in the famous Cromwell tank, which covered itself in glory on the dash from the Normandy beachheads to the Rhine.
The Rolls-Royce organization may well be proud of its contribution to victory. Workers, designers, engineers, management all fulfilled a vital role in Britain's days of need. Now they can once more turn their hands and their brains to the fulfillment of the needs of a world at peace. And this, indeed, they have done. For in October 1945, 2 months after the end of hostilities, it was a Rolls Royce jet turbine that streaked across Britain's luring skies to claim the world's speed record of 606 miles an hour. What promises to civil aviation did this imply? What even newer principles of engine design and propulsion are now occupying the minds of the Rolls-Royce organization? For the world of science has much in store, and in the forefront of mankind's march onward will be Rolls-Royce applying to practice the newest and latest principles of scientific achievement.
I was quite astonished to know what it was because it had no propeller.
And John replied, "Oh, it's easy, old boy. It just sucks itself along like a hoover." There was the awful race against time. There was the skullduggery.
She used to say, "Oh, well, Daddy's doing something very hush-hush."
I thought, my goodness, why didn't I think of this before? And it seemed so obvious then.
A small English church is the last resting place of a man who didn't just change the face of the earth. He enabled us to see what it actually looked like. His name was Frank Whittle. This is the story of how he invented the jet engine. He overcame all the odds, only to see the British government almost throw his idea away and miss a chance to shorten the Second World War.
I was born on June the 1st, 1907 in Coventry. My parents were working class. My father was a foreman in machine tool manufacturers. I lived there in Coventry for 9 years, went for an elementary school there. And then the family moved to Leamington Spa because my father bought a small, very small, engineering outfit called the Leamington Valve and Piston Ring Company. And I really did get my first engineering experiences there because I helped him sometimes for, I think it was about twopence an hour or something like that, making slots in valve stems.
In Leamington, Frank also won a scholarship to the town's secondary school.
I was very lazy with homework and got a series of raspberries for that. But at the end of term, I often do quite well. For instance, I'd come top of maths, something like that. I never did win a prize at school. But I did an awful lot of private study. I used to go down to the library in Leamington Spa and study all sorts of things which are not in the school curriculum. And that was where I first started to learn about gas turbines. I was always attracted to flying from my earliest years almost. When I was 4, my favourite toy, and this was 1911, was a tin model of a Blériot. And my heroes were people like Captain Albert Ball and Major McCudden and so on, the VCs of the First World War, and I just wanted to fly. And also I thought that boys in the uniform of aircraft apprentices looked very good. So I decided I'd like to wear that uniform and applied to join as an apprentice.
The Royal Air Force, however, rejected young Whittle. He was too small.
I was sunk for the time being, but before I left the camp, a very kindly physical training sergeant, if you can imagine such a thing, took pity on me, and he gave me a diet to follow and a series of exercises, Max Alding exercises. I did all that for 6 months. I put on 3 inches on height and 3 inches on my chest. So I thought, well, I'll have another shot. And I wrote to the ministry, but they said, no, once you've been turned down, you've been turned down forever. I thought, well, I go through the whole process again as though I'd never in the hope that the bureaucracy wouldn't pick it up. And I was lucky that time and ended up at Cranwell in number 4 wing.
Whittle didn't enjoy life as an Air Force apprentice. In that rank, he would never get to fly. What brightened Whittle's life was the Model Aircraft Society, where he became the leading light at building working replicas.
So much so that the initials BWMAS, which stood for Boys Wing Model Aircraft Society, was, most people said that meant Boy Whittle's Model Aircraft Society, because we were known as Boy Whittle, Boy Smith, and so forth in those days.
Whittle's skills at making model planes singled him out to the authorities. Perhaps he might be officer material.
There were to be 5 cadets selected from number 4 wing at Cranwell, and I was number 6 in the passing out list. So when the number 1 boy failed because of his eyesight, it made me eligible.
The founder of the Royal Air Force had his doubts, though.
Lord Trenchard nearly stopped it, because I hadn't been a leading boy and I hadn't made no kind of a name in sports, on which a lot of weight was put in those days.
Whittle's CO had a compelling reason to make Trenchard think again.
He thought that he'd got a mathematical genius.
It was this natural gift that got Whittle a cadetship. Less than 1% of apprentices made the huge step to join the elite in the Officers' Training College at Cranwell. Although this was next to the apprentices' wing, it was socially another world, one that shared the culture of the public schools from where most of the cadets then came. In the bleak Lincolnshire countryside, Frank Whittle's life now took a new direction. Cranwell provided a very intensive education for Whittle. For the cadets, just as it is today, a highlight of the course was the flying lessons.
I learned to fly on the Avro 504K. That was a very ancient type of aeroplane, 1911 type, and it sort with a toothpick between the wheels, to prevent it tipping over on its nose, which in reality it helps it to tip it over on its nose, or even turn upside down.
Whittle was soon a daring, even overconfident pilot, and one who had his fair share of accidents.
I have to confess that I wrecked 2 or 3 aeroplanes. 3 at least, yeah. The first one, I got lost and wanted to get back to Cranwell when the visibility had deteriorated very badly. It was the day, incidentally, of the cross-country run at Cranwell, which all cadets hated. And most of my fellow cadets thought I'd done it to get out of the cross-country run.
In between learning to fly and studying at Cranwell, Whittle first conceived the idea that would make him famous. It all started with a student thesis.
All cadets had to write a thesis, and I chose future developments in aircraft design, rather ambitious, and rather concentrated on the engine side. But the main thing in that thesis was that I arrived at what I now know was the well-known Breguet formula. I wasn't familiar with it at the time, connecting speed, range, engine efficiency, and so forth. And to me, that meant that if you wanted to go very fast and far, you would have to go very high, heights of 50,000 feet, that sort of thing, at heights where the piston engine obviously wouldn't work, and at speeds where the propeller wouldn't work. So I started to look for a new kind of power plant.
Whittle prepared this paper during the first half of 1928. But his findings at Cranwell were the fruit of the 5 years he had by now been training there.
My Cranwell thesis, when the professor marked it, he wrote on it, in effect, he didn't really understand it, but he gave me 30 out of 30, which I thought was quite satisfactory.
Whittle envisaged flying speeds of 500 miles an hour, at a time when propeller planes struggled to reach 150. These machines were noisy and shook the pilot terribly. That's because their engines were actually car motors on a bigger scale, with many moving parts. Whittle felt an aesthetic dislike for such power plants.
The problem with the piston engine as you go up height, even though you supercharge it, is that the power drops off as the air gets thinner, and there eventually comes a point where it won't generate enough power to turn itself over against its own friction.
Whittle's idea would use the same principle as a balloon filled with air. When this escapes, every child knows what happens. But it wasn't clear how an engine might recreate such a force.
I considered a piston engine driving a fan inside a hollow fuselage, and then thought, well, why not throw that piston engine away, up the compression ratio of the fan, and substitute a turbine for the piston engine? And there was the turbojet.
By now, Whittle had left Cranwell, but his search for this solution had preoccupied him ever since.
It didn't come to me out of the blue for the simple reason that I've been trying to find it for 18 months. But just the thought, get rid of the piston engine and substitute a turbine, you might say that came out of the blue. Whether I was having a bath or whatever at the time, I couldn't tell you.
Whittle's plan proposed just one moving part. This would be a shaft with a compressor, driven by a turbine at the other end. It would work like this. The compressor spins round, sucking air into combustion chambers at many times atmospheric pressure. Here, this air is mixed with vaporized fuel and ignited. The hot gas created expands through the turbine, turning the shaft, and escapes into the atmosphere. It is this continuous force which propels a jet aeroplane along. The turbojet concept brought with it so many natural advantages.
A very big factor in favour of a jet engine was that when you went up high, the air temperature was very low, very cold, and that benefited the compressor a lot. It meant that you could get much better conditions for the compressor. And the other thing is that in a normal turbine, the velocity coming out of it is wasted. In the case of the jet engine, that was completely used. After the idea had come to me, I thought, oh, my goodness, why didn't I think of this before? And it seemed so obvious then.
This was Whittle's moment of genius. He had seen the future of powered flight, and he was a pilot officer, aged just 22.
I was at the Central Flying School at Wittering, doing the flying instructor's course. One of the instructors there was W.E.P. Johnson, who became a very good friend and colleague in later years, and he'd been trained as a patent agent. And he became very interested in my proposal. He thought it would work, and he helped me to draft a patent.
Have you ever patented anything? No, I don't know a thing about it. Does a patent both publish and protect? That is the whole point of patents. But one thing's essential. File a patent application before touting the thing round. Otherwise, you haven't a hope. I'll tell you what, let's rough out a specification now. What? Fine, what do we do? Well, you make a rather better sketch, and I'll get on with the clever bit, the writing. Okay.
Armed with his patent, Whittle offered his idea to industry. No one thought it could ever work.
According to the theories of the time, there was this fundamental difficulty with gas turbines, inefficient compressors, inefficient turbines, and the other big snag was the materials then existing in 1929 wouldn't stand temperatures of more than, say, about 500 degrees centigrade. But I knew, or felt pretty confident, that they would evolve in the normal course of development, and of course they did.
The positive young officer also went to London to put his revolutionary concept to the Air Ministry. Whittle fared no better when he met A.A. Griffith, one of the ministry's top scientists.
I went to see Dr. Griffith and another scientist at South Kensington, explained the idea. It was very coolly received. Griffith pointed out an error in my calculations, and it was all rather depressing, you know. And then after that, I got a letter from the Air Ministry saying, in effect, that they weren't really interested and so forth. It didn't help that I hadn't then received an engineering degree.
Soon after this rejection, Whittle seemed to have more bad news.
After I completed the flying instructor's course, I very nearly got posted to number 4 FTS, Abu Sweir in Egypt. That would have been a real nail in the coffin of the jet engine if that had happened.
Fortunately, the posting was changed. Whittle remained in Britain and served a year as a flying instructor. These were happy times for him. In May 1930, he married Dorothy Lee. During this period, he also got the chance to develop his exceptional flying skills. He was now one of the RAF's best pilots, and was chosen to fly in the Hendon Air Pageants, where he thrilled spectators with his skills at crazy flying. These were the red arrows of the day, and Whittle loved entertaining the public this way. At this time in Germany, a young scientist was eagerly looking forward to his first trip in an aeroplane. His name was Hans von Ohain.
I always dreamed about the beauty of flying. My first flight with a commercial airplane, I believe it was a 3-engine Yonkers, was a great disappointment. It was so noisy and so vibratory that I felt the piston engine and propeller is not the good propulsion system. The elegance of flying is destroyed by it.
The sight of smoke rushing from chimneys inspired von Ohain to think, if that force could be created by a turbine, maybe he could make a smoother aero engine.
High speed was not the primary goal. To me, the smoothness and low noise was more the starting point of my thinking. But as I thought about it, I noticed that, as a matter of fact, it will be capable of driving the airplane faster.
Britain's Air Ministry had declined to keep Whittle's patents a secret. Freely available, they quickly made their way to Germany, just as the Nazis came to power. These patents were widely read in German aviation circles, at the same time that Hitler was rapidly building a new Luftwaffe. Whittle's idea aroused no such interest in Great Britain, and his own jet engine remained stillborn. Yet the Royal Air Force was certainly keen to nurture its inventor.
After 4 years, every general duties officer had to specialize. He was given a choice between engineering, radio, navigation, physical training, and so on. But I didn't get a choice because, having been pestering the Air Ministry with inventions, they just said to me, "You will be an engineer." Though they'd stopped sending officers to Cambridge, they decided that I should go. So I went to Cambridge in September 1934 to take the mechanical sciences tripos.
Once at university, Whittle applied every piece of learning to his idea for jet propulsion.
I had got the feeling, rather, that I might be ahead of my time. With the extra knowledge I gained at Cambridge, I did become rather more aware of the difficulties.
Then this letter arrived in the post, which says, "My dear Whittle, this is just a hurried note to tell you that I have just met a man who is a bit of a big noise in an engineering concern, and to whom I mentioned your invention of an aeroplane sans propeller, as it were, and who is very interested." He's jotted a note at the top of the original letter. He says, "This letter changed the course of my life and triggered a revolution in aviation." And it did, because this letter rescued the turbojet idea in this country from oblivion.
The writer was Rolf Dudley Williams, an old friend from Cranwell. He visited Whittle at Cambridge with another former officer named Collingwood Tinling.
And they approached me with the idea of forming a company and getting on with it, and they succeeded.
A merchant bank was the catalyst.
Falcon Partners were approached by an intermediary, an engineer named Bramson. William Tinling got in touch with him, and he got in touch with Falcon Partners, and Falcon Partners commissioned him to write a report on the whole project, which he did, and it was wholly favourable. Bramson's report, you might say, was another of the big key points in the whole story. He'd been very much involved with aviation. He was a pretty skillful aeronautical engineer. And his report inspired Falcon Partners to go on with the job. And in March 1936, they formed the company called Power Jets Limited.
Whittle told his backers the project had a 1 in 30 chance of success. The Air Ministry quickly added another obstacle.
One clause said that I was not to work more than 6 hours a week on the job. But of course, that didn't operate as an effective control on me. I worked practically full time.
At Cambridge, Whittle also had to fit in the task for which he'd gone to university in the first place.
And I very much wanted first-class honours. So I had to work like hell because I was designing the jet engine and preparing for my finals at the same time. And that was a very difficult thing to do. I succeeded in getting my first, happily, and then was able to turn back to the jet engine.
Whittle approached a manufacturer in Rugby to build the world's first jet engine. British Thomson Houston made steam turbines. Whittle drove over from Cambridge, rehearsing what he'd say to persuade the huge company to accept a contract. He succeeded, when all he could offer them was £2,000, well below what his project really needed.
The proper scientific way to go about the job would be to build a compressor and test it, build a turbine and test it, build combustion chambers and test it, and then put them all together when the results from each were satisfactory. But the cost for that would have been about £30,000, and there was no hope of getting that amount of money. So the only thing to do was go ahead with the complete engine. What we were doing was trying to prove the engine right from the word go.
In a cavernous Rugby workshop, Whittle set to work on this huge challenge.
The BTH built the engine, and I stood over it more or less while it was going on. I felt that we were going to be all right as far as the simple centrifugal compressor was concerned. I felt that the turbine was going to be all right, but I was uneasy about the combustion problem because we were aiming at 24 times the kind of combustion intensity that was obtainable in those days. But the engine became ready for running proper on April the 12th of 1937. A lot of people said it wouldn't even turn itself over. What did happen proved the very opposite. I gave a signal with my hands to raise the speed with the electric motor to 2,000 RPM, and that was done. And then I opened the main control, and it started all right. It accelerated out of control, and so did everyone standing around it. They all went down the factory like the wind. I didn't, because I was petrified with fright. I just couldn't move. It seemed like perpetual motion, but of course it wasn't. The fact was that a pool of fuel had accumulated in the combustion chamber, which we didn't know about, and that was keeping it running after I'd switched off the control. Well, that sort of thing happened day after day. We had about 4 of that kind of runaway. Just after the engine first ran and we'd submitted a report to the Air Ministry, this was the subject of another report by Griffith, the man who turned the job down in the early days, and his report damned it with faint praise. He brought in all the difficulties, said that no propeller meant that we wouldn't have the slipstream to help us take off, and so forth.
Whittle didn't know that in Germany some people were by now far more willing to bet on his idea. One of them was Ernst Heinkel, a legend in his country's resurgent aviation industry. Von O'Hine had been introduced to him.
He was alone in his villa in Warnemünde. He explained to me that he wanted to finance the whole thing by himself if it works. And he said, I have the best aerodynamicists, I have the best and best designers, and I want you to tomorrow to speak with them and explain your ideas. I loved the Baltic Sea coast very much. I sure would think that would be a nice place to work. And so I choose Heinkel. Additionally, I felt I was afraid to go to engine companies. I thought they were too much ingrained in their recip engines, and my model didn't work sufficiently good.
Heinkel's company was attractive for another reason.
The whole development was very inexpensive, but when we would have asked for more money, we would have gotten it. So money was not a problem.
By contrast, the Powerjet's kitty was empty. As the Nazi threat grew, Whittle had a war winner, yet Britain was set to abandon it.
There were several things which hampered progress. In 1937-38, the worst was the tight financial situation. Our financial backers began to get cold feet. They had, quite unrealistically, expected that within a matter of a month or two, we would have an engine capable of flying in the stratosphere. Well, of course, we had breakdown after breakdown, and they began to lose heart. And they did not produce the money that they promised. The Air Ministry were very hesitant to help because we were in financial difficulty. After we'd first run the engine and shown that it at least was self-driving, they did agree to a very limited contract.
The ministry's grudging help only created new problems.
As soon as they gave us the contract, we came under the Official Secrets Act. That meant that we couldn't tell people what we wanted their money for. You can't go to someone and say, look, we've got a damn good idea, would you let us have some money? We can't tell you what it is, but it's very good. No, we couldn't do it.
By 1939, Britain had spent just £7,000 on Whittle's jet. His very position on the project was perilous. At the end of June, he was actually due to leave Powerjets. On his last day there, Whittle had to impress an important visitor with his engine.
On June the 30th of 1939, we managed to get a big breakthrough in the attitude of the Air Ministry, in that Pye, Director of Scientific Research, came up to see the engine run, and we managed to keep it going for about 20 minutes in his presence, and he became a complete convert. So much so that he agreed that an engine for flight should be ordered, and that an aeroplane to use it should be ordered too. When I drove him back to the station to catch his train back to London, I had the curious experience of him explain to me all the advantages of the engine, that it could run on any fuel, that it was vibrationless, etc., etc. And I just sat quietly. I was only a squadron leader at this time. I thought, yeah, you're telling me, old boy. This, of course, was the big turning point in the whole job.
The turbojet was saved for Great Britain, but Germany, unaware of Whittle's breakthrough, already had a jet plane.
I was very certain that it would work. But, of course, you always feel there's a danger. And we had made not too many pre-tests. We ran the engine before it flew perhaps several hours at the very most.
The support of a huge aircraft company had enabled Hans von Ohain to overtake Whittle. Heinkel's HE-178 was ready just days before war broke out. Test pilot Eric Varsitz was eager to take off.
He started and then he disappeared. And after a while he came back and we thought, oh, he's landing. He didn't. He made another round and we said, oh my God, he must like it. But we didn't have the airplane very filled up with gasoline. He landed and stopped the airplane just where Heinkel stood. And he said everything functioned beautiful and the engine worked well. And he was really himself, very enthused. We had a nice festival.
A jubilant Heinkel rang General Ernst Udet at the German Air Ministry.
I learned later on he called Udet and he said, hey, congratulations, but let me sleep. That's an ungodly time.
By now, Frank Whittle had been forced to move power jets from Rugby to a scruffy foundry at nearby Lutterworth. Ladywood Works was the name of the site. Today, there's nothing to show that history was once made here. But in these buildings, Britain slowly expanded its jet program.
In 1939, we only had just a handful of about half a dozen. And at the beginning of 1940, we began to build up a team, and I was very careful in picking real quality. You know, first class honours Cambridge, first class honours Oxford, Imperial College of Science. We were advertising. Of course, we couldn't say what we were advertising for. And when we were interviewing them, we couldn't tell them what we wanted them for, although I think some of them guessed from the questions we asked.
Whittle's charm and enthusiasm at once inspired his new team to strive for the impossible. The noise and lack of space at Ladywood forced Whittle himself to work at Brownsover Hall, a country house nearby. Here he worked through the night, desperately aware that his work could shorten the war, and drove himself to nervous exhaustion.
My memory of him really was just somebody always working. And when he was at home, if he took any time off, say Sunday, he would sit in his chair by the fire at Broomfield and we'd be there with his slide rule, which of course people used in those days to do their calculations, and bits of paper all over the place, working, and a little bit of time for myself and my brother, but not much, not much.
As Britain entered its most critical phase of the war, the expanding team at Ladywood was galvanized by a new order to prepare engines for a prototype jet fighter. Codenamed F940, we know it as the Gloucester Meteor. As a potential war winner, getting it in the sky to fight the Luftwaffe now became the focus of their work at power jets. They did not know that Germany was by now developing its own twin-jet combat planes at Messerschmitt and Heinkel. The country's prototype jet, the HE-178, had not been a success, but its last flight was exploited to the full by its maker.
Heinkel invited the Air Ministry to come, and the highest who came was Udet, and somehow Heinkel used that possibility to offer a new design of a two-engine fighter aircraft. And actually, he got the contract about 2 months later.
The plane was the HE-280. The Nazis wanted it in 14 months. Heinkel passed this demanding deadline to von Ohain to build its jet engines.
Or Heinkel wanted things very fast. He was very optimistic, very positive, but a little bit unreal and unrealistic in his time schedules.
In Britain, the Air Ministry still wouldn't fund Frank Whittle properly, forcing power jets to work in impossible conditions.
In addition to our continuing financial problems, we had many others, like having to use the same parts over and over again when they ought to have been scrapped. And of course that was linked with the finance because we couldn't afford new parts. We had to make do and furbish up damaged parts.
Some people continued to claim Whittle's jet wouldn't even fly. By May 1941, his engine was ready to go in Britain's first jet plane, the experimental Gloucester E-28-39. For its maiden flight, the top-secret aircraft was taken to Cranwell, where the jet story had begun. The Power Jets team followed, full of hope. On the same day, a young naval pilot, Eric Brown, was forced to land at Cranwell. Today, he's one of the few surviving witnesses of this historic occasion.
When I landed, I was a bit astonished to find so many civilians present. And when I went to check in at the mess and asked what was going on, there seemed to be almost an air of conspiracy about the whole place. And nobody would give a straight answer to this.
We'd been out the day before for some taxiing trials. And then on May the 15th, the weather looked as though it wasn't going to work out. So I went back to Lutterworth.
That morning I went to Control Tower to check if the weather was good enough for my en route flight to Croydon, but it obviously wasn't. And they said, would I mind doing a weather check for them? Anyway, I landed, and they said, would I be prepared to do a further weather test in the afternoon?
And then we got a message to say that the weather was clearing, so I rushed back to Cranwell again. And in the evening, Jerry Sayre did the flight.
An airplane was rolled out with a shape well, not so much the shape, but the construction of which I'd never seen before because it had no propeller. And an extraordinary whining noise came from it, and it taxied out to the end of the runway, and after a while eventually took off. And I was quite astonished to know what it was, because I'd never heard at this stage in my career of a jet aircraft.
The various government ministries refused to film this remarkable event. Luckily, an unknown photographer grabbed it in secret.
Jerry Sayre was sitting at the end of the runway, and a party of us was sitting just to the right. And he held it on the brakes and ran up the engine to full speed, released his brakes, and then he hopped off in about 600 yards. Quite an impressive takeoff. And he held it down level and then glide. One of my colleagues, Pat Johnson, W.E.P. Johnson, slapped me on the back. He said, "Frank, it flies." And in the tension of the moment, I rather rudely said, "That was bloody well what it was designed to do, isn't it?"
And it landed successfully, and immediately it landed, it was absolutely inundated with people rushing out and congratulating the pilot. So I realized something quite extraordinary had taken place.
People in the area hadn't heard that particular kind of noise before, and you couldn't really hide it, however secret it was supposed to be. One officer was said to have asked another one, "How does that thing work, John?" And John replied, "Oh, it's easy, old boy, it just sucks itself along like a hoover." Another story was that someone who claimed to have been an eyewitness said there was a Merlin engine inside the hollow fuselage with a little propeller. And he'd seen it. He was a reliable witness, he claimed.
Well, everybody gravitated towards the officers' mess. And so I followed on, and there was quite a lot of hilarity going on in a corner of the room. I asked what it was all about, but still nobody would reveal what was involved. But it was quite obvious. It was something quite momentous.
The flight vindicated Whittle. Britain's new jet plane was better than anybody had realised. One event particularly brought the point home.
The ministry gave us permission to open up to 17,000 just for one flight. And at that engine speed, it did 375 or 380. Anyway, it was faster than the Spitfire.
The news reached London and Winston Churchill. He ordered 1,000 Whittles. Alas, the E-28 could not be a warplane, hence the disappointment felt behind the scenes up at Cranwell.
I would have preferred it to have been the Meteor, which was then on the stocks, because that was the combat aeroplane, whereas the E-28 was just an experimental aeroplane.
Whittle's jet served notice on all piston engines, a notice that fast reached their manufacturers. They now demanded their share of a product none had invented, and which they'd rejected for years. Because of the war, Whittle would have to share his secrets with them.
All this, of course, was putting power jets into a weaker and weaker position from the commercial point of view, And that we had to swallow because it was a wartime situation. And I and several other of my team were serving officers. And we had to put national considerations before commercial considerations. That was very dominant in my mind.
Whittle played a selfless, patriotic role, in which he offered his knowledge freely to the British aviation companies. However, they were working flat out to build engines for planes like the Hurricane and the Spitfire. So in 1941, Great Britain turned to the United States, then at peace, for backup in manufacturing its jet engine. The Americans had only been told about Whittle's power plant earlier that year. Ironically, their top scientists had dismissed the concept in 1940. They concluded the gas turbine engine could hardly be considered a feasible application to airplanes. The British government expected to keep the rights in Whittle's invention, and did not intend to give it away to a future competitor. But that's inevitably what happened.
We shipped over the engine in parts in the bomb bay of a Liberator, also with the team, who were horribly frightened unless the pilot should pull the wrong lever and they'd all drop into the Atlantic.
The company selected to build the engine was General Electric.
For America, the jet story began the night of October 4th, 1941, with the arrival of a highly secret engine assembly at a Boston airport. It was Britain's now famous Whittle Turbojet, the first jet engine successfully produced and flown by the Allies.
Gentlemen, I give you the Whittle engine. Consult all you wish and arrive at any decision you please, just as long as you accept a contract to build 15 of them.
General Electric had that engine, their engine version of the W2B, called the Type I, on test in April of 42, so just rather less than 6 months, which is astonishing. And even better than that, 6 months later, the Bell Aircraft Company had their twin-engine jet flying. It was agreed that I would go over and help them out. And so I went over at the end of May. I went to Lynn under an assumed name. They insisted I use an assumed name. I called myself Whittle. There were times when I forgot it, like in the hotel I would waking up, sign for my early morning coffee, and forget that I was supposed to be using an assumed name, and of course sign the real one. I'm told that that didn't matter really because the waiter was an FBI man.
In the Great Republic, Whittle was treated royally, and he in turn was astounded by what he found there.
It was most satisfying to see the work GE were doing because, well, they got on with the job so fast. It was remarkable, and their enthusiasm was most inspiring. And I thought at the time, if only I'd had that kind of cooperation a few years earlier, what a difference it would have made.
In America, doctors found that Whittle was by now battling with severe ill health. Back in Britain, the problems that caused it had only got worse.
The engine that was destined to be the power plant of the Meteor was a more powerful version of the experimental engine, really. There were no major difference. It looked quite similar from the outside.
The Royal Air Force eagerly awaited the Meteor, but Powerjets was not allowed to produce the engines for it. That job had been contracted to a car maker, Rover.
Glossers were getting on with the job fairly well, but Rovers were making an absolute nonsense of the engine. They just hadn't got the people who could do the job, and they thought they knew what to do. The situation became so bad that it looked as though there would be a complete hash of everything. The Rover were making such a poor job of the engine that the order for the production of the Meteor was cut right back.
Rover tried to redesign its engines and held up the Meteor by 2 years, but there was also dirty work.
We intended that the Rover company should be subcontractors and only subcontractors, but unfortunately they went behind our back to the ministry and tried to get direct contracts, and eventually they succeeded in doing that. And instead of being subcontractors to us, they in effect became competitors who had the advantage of having all our information handed to them on the orders of the ministry.
In December 1942, a solution was at last found to the problems with Rover. Rolls Royce took over the job of building Whittle's engines. But the mighty company would only weaken power jets further.
Ernest Hayes was the chief executive of Rolls Royce. He was responsible for the Rolls Royce part in taking over the jet development, because he had come to realize that this was the future of the aero engine. And since Rolls Royce then were one of the most prominent aero engine firms in the world, he wasn't going to be left out. I would call him an honest rogue, because when he was going to do the dirty, he told you he was in advance. And one of the things he said to me on one occasion was, he said, "We're going to be the center of this job, and nothing you can do will stop us." By 1943, the Rolls-Royce having made such a big difference to the prospects of the engine, the ministry agreed to reinstate the production of the Meteor.
With Whittle's engines, the plane finally made its first flight that year. Yet it should have been ready 2 years earlier. And had the Air Ministry pursued Whittle's idea back in 1929, a similar plane would have been available by the start of the war to repel the Luftwaffe. Lives would have been saved. The war even shortened. At least the work of Frank Whittle could now have a bearing on how that war was fought.
I thought that he was doing something quite important, because every time I asked my mother what he was doing, she used to say, "Oh, well, Daddy's doing something very hush-hush." I didn't become aware that he was anybody out of the ordinary until 1944 in January, when they made the whole thing public. And then the house became surrounded by reporters.
We had been working in complete secrecy until early January 1944, at which time, for reasons I don't really know, the British and American governments decided to make an announcement about it. It was like the world blew up around me. The shock was very considerable.
Whittle and his engine dominated the front pages.
Says here in the Daily Herald, "I knew Frank had a secret," says his wife. So the cat is out of the bag. How strange it seems to be able to talk about it. "It may mean that I shall be known throughout the world. In any case, my younger son, Ian, is a far brighter boy than I was at his age. I think he will be a success, the success of the family."
Have you seen that?
No, I've never seen that before. Oh dear, how wrong.
As industry reaped the rewards of Whittle's genius, new jet fighters joined the Meteor. First off the drawing board was de Havilland's brilliant Vampire. The pilots loved their new equipment, although the planes remained highly secret, as Eric Brown discovered when he came to fly them.
When I was allotted to the jet flight at Farnborough, of course it was a top secret flight, and it was in a hangar at the far side of the airfield, well away from the main activity, and there were RAF regiment guards there with guard dogs, so it was very highly guarded at the time.
Once inside, the plane was a revelation to Brown.
We're getting into the cockpit of a jet airplane for the first time. You are struck by the wonderful view, because in a tricycle undercarriage, no propeller or large engine ahead of you, it is quite remarkable. And once you start up the engine, although to listen to a jet, if you're outside the cockpit, it sounds thunderous. When you're in the cockpit, it is incredibly quiet.
Frank Whittle often visited Farnborough to check how his invention was performing.
It was quite obvious he was itching to get his hands on it and fly it. But we were always alerted that he was coming, and a little memo would be passed round saying, would you make sure that the 2839 was not serviceable for flight on that particular day? And because this would stave off Frank, it was obvious they didn't want this wonderful airplane and this wonderful man to be united in case there was an accident. So he twigged this pretty soon, and I think he played along with it.
In July 1944, the Gloucester Meteor became the first jet fighter to enter operational service, when the Air Force allocated its initial supply of planes to 616 Squadron at Manston in Kent. By now, the Luftwaffe could no longer mount air raids over Britain, but these meteors were quickly put to work, intercepting a lethal new menace, the V-1 guided missile. Germany's flying bomb terrified the Londoners who were its target. In the skies over Kent, the meteor pilots sought to prevent V-1s reaching the capital. Some used their wingtips to flip the missile over, so it crashed. Around this time, Allied pilots were startled to find themselves being attacked by a German plane with no propeller. This was the Messerschmitt 262. Germany's own jet program had by now advanced to this sophisticated design. It had been chosen instead of the HE-280. The Nazis never liked Heinkel and had cancelled his promising jet fighter. Yet it could have been mass-produced by 1944. By contrast, the 262 arrived late and was rushed into battle too soon. In Britain, meanwhile, Frank Whittle seemed at his peak. He was a national hero, while his company now had a custom-built factory from which to expand. He had a clear vision for its future.
I always wanted to include manufacturing in our duties. In 1944, our power jets had reached the point where they were able to produce, say, batches of 40 or 50 engines. And we had a first-class nucleus for proper manufacturing organisation.
Power jets also had some outstanding work in progress. Whittle was already planning the second generation of jet engines.
There was the LR1 turbofan, which would have been the first turbofan in the world. There was the engine for the Miles M52, the supersonic aeroplane. Those were our two big projects which we had in hand.
LR1 stood for Long Range 1. Whittle saw the scope for jets that would fly planes further as well as faster than pistons. But he would need a more efficient engine.
From the earliest days of the turbojet engine, I was bothered by the fact that it has a basically low propulsive efficiency, about 50% as compared with, say, a propeller at moderate speeds of 80%. And so the answer to me was that we must gear down the jet in some way. And that led to the concept of the turbofan, for which I took out a patent in 1936.
The turbofan is a turbojet to which a fan has been added. This fan causes air both to flow through the core of the engine and to bypass it. This additional jet of cold air increases thrust and improves fuel economy. The design had huge potential.
With a turbofan, you can expect propulsive efficiencies of 75% or even better if you have a very large bypass ratio.
As piston engine bombers approached their design limits with planes like the Lancaster, Whittle saw a timely use for his new bypass jet.
As the war progressed, in 1943, for example, I came to the conclusion that it could be the answer to a long-range bomber for the Pacific War. We also visualized it as an engine for a transatlantic aeroplane.
Whittle was already predicting long-range jet airliners and the kind of engines they would need. But it was the other power jet project that would grab people's attention.
The engine for the supersonic plane, the M52, was an aft fan with afterburning, all tacked onto the back end of a W2700 jet engine. And that should have given sufficient power for the Miles M52 to do 1,000 miles an hour. I think it would have done it.
Despite its huge potential, Whitehall never felt comfortable with power jets. It was a private company, but its driving force was a serving officer, and it was publicly funded. The fault lines were clear.
I realized that there was a complete mess from the contractual point of view. There were no effective agreements, and no one except power jets had risked any money, except the government, of course. And I felt that the government, having put in $2 million, that all the companies should be nationalized, forming a collective turbojet establishment, and of course I hoped that power jets would be at the top of the pyramid, with myself as chief engineer.
Whittle's proposal was considered in the high levels of government.
Sir Stafford Cripps, the Minister of Aircraft Production at that time, used what I'd said to get the ministry out of the mess that they'd created by nationalising power jets only. which relieved them of all their undertakings.
It was expected that Powerjet would still continue with its advanced engine projects.
But then other firms began to create difficulties. They said they weren't going to have the government competing with private enterprise. So considerable pressure was brought to bear on the ministry.
And the minister caved in to the large aero engine companies.
So we, the people who had pioneered the whole thing, were deprived of the right to design and build engines. Sorry. That was too much for myself and my leading team members, and most of us resigned.
The supersonic plane and the turbofan project had by then been cancelled. The civil servants found a reason to justify this loss.
Believe it or not, the minister said that people wouldn't want to fly at speeds more than about 250 miles an hour.
As Whittle left Powerjets, he was acutely aware of the commercial opportunity that was now at stake.
The position in 1945 and 1950 was that Britain was really ahead of the world in all forms of gas turbine development, but stupidly we allowed the lead to slip away.
In 1945, the Allies discovered the Germans' impressive range of jet planes and their designers.
After the capitulation of Germany, I was at that time in Farnborough the CEO of the captured enemy aircraft flight. So I was sent to Germany and to look at their advanced aircraft, and also at the same time to interrogate their designers and test pilots. Amongst them was von Ohain, and naturally I wanted to know what his connection with the Whittle patent had been in Germany. But he was not going to answer this question. He was very non-committal and sidestepped it as much as he could.
Brown flew the various German jet planes, including the Messerschmitt 262. The Allies already knew that its engine, the Umo 004, was a sophisticated axial flow design. Now they could compare its performance with that of the less complex British jets.
So a more efficient engine in many ways. It was highly unreliable. The Umo 004 in operational service had a scrap life of only 25 hours. And the engine, when I flew this engine, I found it extremely sensitive and difficult to handle because it did not like quick throttle movements, either accelerating or decelerating. Any quick throttle movement, either way, could possibly cause a flame out of the engine.
Whittle's jets were more reliable, but he could take them no further. The course of events brought anguish.
I think my mother was most distressed by what was happening to father. She was most distressed. I could remember her crying about it at times because she would tell me, "Oh, Daddy's so unwell because of what's happening, and it is such a shame, and how can they treat him like this?" Yes, it's very sad for her. He managed to soldier on in the RAF, and he was an Air Commodore in 1946, but in the end, by 1948, he'd been declared as unfit for flying, and somehow that was the last straw, and he and the RAF both agreed that he should retire, and he did.
It's been very sad for him.
Oh, very sad, yes. The Air Force was everything to him.
The public knew none of this and saw a war hero receiving his just rewards. In 1948, Whittle went to Buckingham Palace to collect a knighthood. He also had a financial award for his invention, which was good for the time. Worth nearly £3 million today, it would soon become clear he was greatly under-rewarded. He sought a role, but his stature made him hard to place in an industry he himself had founded. No engine maker hired his services.
In many ways, I paid quite heavily for the work I did. There was the awful race against time. That dominated life. On top of all the technical difficulties, there were the financial difficulties, there was the skullduggery of people who were messing things up, and it was frustration after frustration, and it took its toll. I began to have a series of nervous breakdowns, and for years, it was years before I really recovered my health.
Britain stole a march on the rest of the world when it launched the first jet airliner. The beautiful new plane, with its 4 engines, was a fruition of all Frank Whittle's early visions.
First, after he left the RAF, he turned his mind to the introduction of the Comet, and he joined BOAC as a consultant to help them introduce the Comet into service. He was very worried at the time that the thing was being rushed into service. I've got his 1949 diary where he discusses the strength of the square windows, and he was worried about that at the time, and was making a suggestion to de Havilland's on how they could get over the problem.
Whittle's advice was ignored. The Comet crashes which followed were caused in part by its square windows. With time on his hands, Whittle travelled and tried to recover his health. He also turned to writing his memoirs. The jet age took off without Frank Whittle, but the Royal Air Force was soon re-equipped with the benefits of his invention. By 1950, the Gloucester Meteor provided the backbone of Britain's air defence capability. It was a fitting outcome to all the secret toil of the Power Jets team in the dark days of the war. The nation did at last build its own supersonic fighter, in the shape of the English Electric Lightning, while jet engines also powered an awesome British fleet of nuclear bombers. But the country could never really afford such planes. They would later play an important role in the Falklands campaign, but were destined to become museum pieces. British civil jet planes fared little better. After the Comet crashes, it was Boeing's 707 which brought long-range jet travel to the masses. By 1960, airlines were mostly buying their planes from America. That year, the bypass engine entered service. Turbofans soon followed. With their far better fuel economy, they were just what the airlines needed to realize low-cost global travel. For Frank Whittle, it was the ultimate vindication of his wartime vision, and revealed the sheer folly of cancelling his pioneer turbofan. Yet he never worked on jet engines again, and memories began to fade of how the story had begun.
I think in this country they were beginning to forget all about Frank Whittle by the 60s and 70s.
It was all so different in the United States.
They were so much more gung-ho. They were very good at slapping him on the back and telling him what a good chap he was.
In 1976, Whittle went to live in America.
I think he felt more recognised over in the States than he did over here.
After the war, Hans von Ohain had himself moved to America to work on jet propulsion for the US Air Force. Fascinated by each other's work, Whittle and von Ohain became good friends. Back across the Atlantic, Britain eventually rediscovered its genius of the jet.
By 1986, even the Queen took a hand and awarded him the Order of Merit. And other honours came along following that. So I would say from about the early 80s onwards, people began to remember who it was who was the prime pioneer of the turbojet.
And also a man with a profound legacy. Today, we make almost 1.5 billion air passenger journeys a year, cheaply and safely, thanks to Frank Whittle. He shrank the world, but his gift to Britain is less appreciated. Its famous plane makers have departed, but today, Rolls Royce is a world leader in building jet engines.
I'm often asked how I feel about it, and it's a question I find very difficult to answer. things could have been a lot better. We could have had a much bigger influence in the war than happened. But when I see what's happened in the way of civil aviation and military aviation too, but particularly civil aviation, I can only say it's extremely satisfying, especially when you see something like the Concorde. And one of the things you see I never foresaw when I was working on this thing is that I would be a passenger crossing the Atlantic in 3.5 hours. And incidentally, another thing I didn't foresee is that I would have a son who would be flying 747s as a captain in Cathay Pacific.
Kai Tak Aerodrome at Hong Kong had a very interesting approach, a curved right-hand turn right down to almost a touchdown. And when Father came with me in the back of in the cockpit in a Boeing 747, he was very startled when he saw that his son was flying an airplane at 1,000 feet straight towards the foothills and then making a steep final turn, which of course was quite normal at Kai Tak. It was the way you had to do it. I hadn't briefed him, unfortunately, so he was very white-knuckled by the time we landed. He was continuing to theorize in aerodynamic improvements and aero engine improvements until the end of his life. He always took an active interest in Concorde and looking into a second generation SST, supersonic transport, and making recommendations and speaking publicly and privately amongst the industry to try and encourage the airframe manufacturers to take the risk and embark on another generation of supersonic transports.
Concorde is a marvelous airplane. I've flown it many times, but I'm looking forward to the next generation of supersonic transports, which I think should be capable of carrying 300 passengers for distances of the order of 4,500 miles, like San Francisco, Tokyo, at speeds of about a Mach number of about 2.3. That's getting up to 2,000 miles an hour, as compared with the Concorde's 1350. But beyond that, I think we're going to see even much higher speeds than that in due course. Unfortunately, they're going to be very expensive propositions.
Sir Frank Whittle died in August 1996, assured of his position as the greatest aero engineer of the 20th century. The Royal Air Force paid fitting tribute to its distinguished son with a memorial service at Westminster Abbey.
He and I had wanted the opportunity to fly together, preferably in an open cockpit biplane, so that together we could loop and spin and climb and dive. This modest ambition was never realized for one reason or another. The nearest we got was when I flew him to Hong Kong in a Boeing 747. On the last morning of his life, I leant over his bed and said, "Dad, let's put on our kit and go flying." He opened his eyes and looked at me and smiled. That evening, with Hazel holding his hand, he died. And I wondered if he went flying, and if he did, if he went on his own, or did he have a companion? he was cremated in the USA, and the air attaché there brought his ashes over to this country. And I went to Heathrow to meet the aeroplane, and I came home and put the ashes on the bookshelf in my study with the ashes of my mother, who died 3 weeks earlier. I decided to put them in at the Church of Cranwell, and they organized a meteor and a vampire. So we flew the ashes up to Cranwell, and they were interred there with a little ceremony.
I guess as a young physicist, I had no inhibition of thinking anything I wanted. And I flew with the commercial airplane. I believe it was a 3-engine Yonkers. And it was so unbelievable noisy and vibratory that I had the feeling it's a very unfortunate combination, the piston propeller with the airplane, all the dreamed elegance and smoothness of flying seemed to be driven out.
Did you at that time know anything about compression ratios and turbines and operating temperatures?
No. I thought what is required is an aerodynamic flow of gas to drive in a steady fashion the airplane. And much later, when I began to make calculations, I became aware of necessary pressure ratios and these relationships. But about turbines and compressors, I did hardly know anything at that time.
And had you known, would it have inhibited you? Would it have stopped you going on?
It would have perhaps brought me right away to the gas turbine. At the beginning, I didn't know that a gas turbine would be the right thing. And I didn't know anything about gas turbines, as good as nothing. As a matter of fact, I wasn't even sure what this process should be. It was rather nebulous, but pretty soon when I started to think more strongly about this idea, I became aware of many possibilities, and my education in physics and in thermodynamics. I had a minor under Prandtl in aero and thermodynamics. And so I began to think along the lines how to produce a steady flow with a good efficiency. And slowly it came that my mind became clear that pressure ratios and temperatures and velocity ratios are very major factors.
And this, as you describe it, this is evolutionary, really, isn't it? You didn't have a streak of inspiration so much as an evolution of your thinking, right?
Not really. I hate to tell you what gave me the push in the direction, because it is really a more layman's approach. I walked around in Göttingen on the city walls and saw that strong chimney blowing, and that gave me the idea suddenly, you know, the gravitation gives you a certain pressure, and the hot air is not so much under the gravitational influence, and so the chimney is a kind of a thermodynamic process. Now, as a physicist, you know then that it's a very relative thing whether you have gravitation or inertia. So when you had a U-tube rotating, and would take one leg of that U-tube and heat it, heat the gas in that other leg, then you have really a strong gravitational field and therefore a very strong flow of hot gas in a rather small embodiment. And that was the reinvention of what the physicist Nernst invented already in 1912, which I learned much later. That was the so-called Nernst, N-E-R-S-T, Nernst turbine. And but before I knew that, I already departed from it because I thought it is not possible to have a combustor rotating with high speed.
Did you, in the first place, did you start off from theoretical principles, or did you just go and make something?
No, I went to the theory of how can you produce flows. As a in theoretical physics, you learn, for example, that when you have very small particles which are heated on one side and cold on the other, they produce an enormous thrust if the particles are smaller than or in the same order magnitude of the mean free path. And you know, we had in any window or show window usually that little mill which rotates when heat is radiated on it, because the black side gets hot and the non-black side stays cold, and that is then rotating very fast. Now that principle I learned very quickly is impossible to utilize because the mean free path is too small. And so I came to other ideas, and finally it brought me to the thing with the chimney and with the rotating machine, the Nernst turbine. And from the Nernst turbine, I noticed you cannot have a rotating combustor in high speed. So I cut it off and had a compressor wheel and a radial inflow turbine.
You wanted something, in other words, you knew that you wanted something that would flow.
Yes, yes.
That
was now a thermodynamic machine.
Can you tell me how you came across Max Hahn?
Oh, I had a little car, an Opel open sports car. And I went always as a student over the weekend into the snow mountains of the Harz, which is about 50 kilometers away from Göttingen. And Hahn was a machinist in the garage where I had my car. He came and talked to me sometime and said, how come that you always come home without any scratch? And most people, when they come home, have here and there made an accident and so on. Well, I was pretty good in car driving in snow. And the man, we talked then often about two-cycle engines, and he knew very well, he made the impression to me that he was greatly interested in engineering aspects, but he was only the head machinist. So when I had the idea of the first gas turbine type, I thought I have to make a patent and I have to make a model and to prove that it works in order to sell the idea. And I thought suddenly of Max Hahn, that he would be the only one I know who would probably be capable to build it. And so I came together with Max Hahn.
What were his gifts?
Well, he knew, from my standpoint, enormously much in machine working. He had a good knowledge in materials and in processes. So he was more or less a kind of an machinist with an obvious gift for engineering.
What type of engine did you make at Bartels and Becker?
It certainly was not supposed to be a prototype engine. That would have been too ambitious. But a model, I thought, which would show that the principle is working, that the combustor works, that the machine runs self-supportive, and you need only a small horsepower to start it, and then it runs by itself.
And this is what Max Hahn made, presumably, out of materials which you supplied, was it?
Yes, we bought it. Max Hahn and I, we thought the turbine side, we need heat-resistant material. And we could find in catalogs sheet metals, which we could buy, which I could buy. And we had on the turbine side sheet metal, which was heat resistance, on the pressure side, normal construction steel.
This was, from your point of view, you were a physics student working on a PhD thesis, which strikes me as rather abstract, but in fact you did something tremendously practical, didn't you? Was this because of your temperament?
No, I do believe when I went into the engineering side, I always wanted something extremely simple. When my Professor Pohl asked me before the doctor thesis to make a simple apparatus demonstrating refractory materials, I came up with such a simple device that he was very enthusiastic and took it right away into, let it be built, and took it into his physics model arsenal.
Now, I think when your demonstrator actually fired, Max Hahn said something rather amusing about it, didn't he?
Yes. Max Hahn, in his heart, did not believe that the machine would run. Now, when we had the machine driven by the little starter motor, and I saw that the burner didn't work because all the flames leaked out as yellow flames, which told me right away that the burners didn't work, and I was disappointed. Max Hahn, however, was, to my greatest amazement, not at all disappointed. He said, my God, the starter motor lost a lot of power. In other words, the machine almost wanted to run. And also he said, and look, the flames came out with high speed at the proper side, namely at the turbine side, and not on both sides, what he probably thought on the compressor. So I felt that was amusing and showed me that a pessimist like Hahn was more elated than I was with the results of the first tests.
Essentially, was it an evolutionary idea or a flash of insight?
Honestly, I would think it's a combination of both. Because the goal was already there. I wanted to invent something which drives an airplane. Then I was looking for various processes which could do that, and most of them I rejected. And then the idea with the reinvention of the Nernst turbine was triggered by seeing that chimney. It was triggered, it wasn't really, so it was then very quick going into the Nernst turbine. And from the Nernst turbine, the logic told me you cannot rotate a burner so fast in one leg. You cannot produce the combustion properly. So you have to cut the machine off and put the burner still standing. That gave me the idea you have to have little ramjets, so to speak, as burners in the housing. So it is a combination of revolutionary, or I should say immediate thoughts, non-evolutionary thoughts, and evolutionary thoughts.
Were you pursuing the goal of high speed, particularly at that time?
I thought more this. The high speed was not the primary goal. To me, the smoothness and low noise was more the starting point of my thinking. But as I thought about it, I noticed that, as a matter of fact, it will be capable of driving the airplane faster. And because I thought the weight would be very light and the power output would be very large. And so I more and more drifted over in an evolutionary fashion, particularly when the Heinkel people told me that their only goal was higher speed, and they could care less about the smoothness and absence of vibrations, which was my original thought. So it's very hard. It grew into the direction, but it was not the starting point.
What did Professor Pohl say to you that struck you as particularly timely or appropriate?
He said, "You are doing the right thing using physics to create new technology. That's what I like. I dislike, however, when they use it to make out of technology a science with lots of equations and lots of investigations not leading to any new thing."
How come that you came to go to Ernst Heinkel?
Well, I studied a third semester, I believe it was, or fourth semester, in Rostock. And I loved the Baltic Sea coast very much. I learned about Heinkel as a man who was for swift airplanes and very unconventional guy. And later on, I put the two things together. The unconventional airplane man and the beauty of the Baltic Sea. I sure would think that would be a nice place to work. And so I choose Heinkel. Additionally, I felt I was afraid to go to engine companies. I thought they were too much ingrained in their recip engines, and my model didn't work sufficiently good. In fact, it didn't work at all. And so I thought Heinkel would be the right place.
I think that, in fact, what happened was that Professor Pohl put you in touch with Heinkel, didn't he?
When Pohl saw my predicament, he wanted to help me, and he said, "I write a very nice recommendation letter because your ideas, which I had read and your mathematical derivations are all right, but you need industrial support. You cannot privately finance combustion, which I agreed very strongly. And then he said, you know, the best thing is I will write the letter of recommendation and bring you together rather than you, because when I do it with my reputation, I can help you very much, which he did.
You went to see Ernst Haenkel. Was he alone the first time or in company?
He was alone in his villa in Warnemünde. He asked me questions, what one could do with it. He explained to me that he wanted to finance the whole thing by himself if it works. He said then, which reminded me almost on a circus manager speaking about his artists who jump the ropes and so on. He said, I have the best aerodynamicists, I have the best and best designers, and I want you to tomorrow to speak with them and explain your ideas. So with that, we parted. Next day I came to was confronted with his engineers. He was not present. And I got acquainted with the very famous two brothers Günthers, with a man, Dr. Mattes, from the experimental area, with an excellent aerodynamicist, Helmbold, who came later on here to the United States, and others, and Schwerzler. Yeah, Schwerzler was the designer. And in order to make the story short, after I explained and after I showed what my performance predictions theoretically were, the verdict was as follows. Siegfried Günther and Walter Günther, both, they enjoyed the fact that we don't have a propeller. They warned, however, that the engine should be in diameter much per horsepower, should be very small in order to compete with the current great improved recip engines. The Schwerzler, who was the designer, said, oh, when that engine would ever work, it would be so much cheaper and lighter and simpler. That would be wonderful. And Dr. Mattes from the experimental section said he knows a little bit about turbine, and he came to values of that turbine which were not as favorable as mine, but still well enough to be of value for future aircraft potentialities, which made me very happy. But I did not get around why actually he came to these less good values. I learned much later, and not even from him, that my component efficiencies, which I had assumed were far too optimistic, Helmbold later on discussed that with me about a month or so later.
Can I put this to you tactfully? How old were you then? You were very young. Didn't they treat you skeptically?
Yes, they did. I was then, I believe, just 24. When I started out, I was about 21 and shortly before 22. And in the stage I met Haenkel, I was 24.
And to be treated skeptically?
Yes, but Haenkel did not treat me skeptically, because that Professor Pohl's letter must have made an enormous impression, because I actually had succeeded with other things.
What kind of man was Heinkel to work with?
Well, Heinkel wanted things very fast. He was very optimistic, very positive, but a little bit unreal and unrealistic in his time schedules. He wanted things too fast.
What were the circumstances in which you were employed by Heinkel, first of all?
Heinkel offered me a preliminary contract where he would pay my expenses, which I had to income tax pay myself, not as an employee of the company. And as soon as success shows, then he wanted to give me what I wanted to have, a royalty contract and an employment contract. And that was the situation.
And Max Hahn was to come with you?
I wanted to have Max Hahn and got difficulties later on with the employment office. They said, you cannot do that. That man has a good position at Bartels and Becker and Göttingen, and God knows what comes out of your whole project. And I talked with Heinkel, and Heinkel said, oh, they're crazy. Naturally, he comes. Because even when the project doesn't work and work out positive, I can always have a very good mechanic, and I like that he's coming to us too, and that settled the case.
In fact, of course, you are now really moored in circumstances of great secrecy, weren't you?
Yes, the secrecy was that he didn't want that we talk to anyone, even to the Air Ministry. So it was a secret except for him. It was against the his own factory, the Air Ministry, and against anything else except him. And so he wanted that we have a location apart from the whole company.
This was really to protect you, was it?
Well, I think, I'm not sure whether it was to protect me. It could be, but I think his main objective was that he didn't want that the Air Ministry hears about it. At that time, I didn't know it. At that time, I thought that was a very idealistic view. Much later, I found out that the Air Ministry would have stopped him right away.
Why so?
Because he was an airplane company, and Germany had already too many engine corporations. They had the Bramo, they had the BMW, they had the Daimler-Benz, they had the Junkers. That means 4 major companies, and the Air Ministry was trying to cut one already, namely Bramo.
Yes, can you tell me how much the original model cost you to make?
The model itself, without the burners, was about 500 marks at that time. And I owe thanks to Max Hahn, who had, through helping in the design, simplified it to the point that it could be done with his machines and in that short time. The burners, the little stationary ramjet burners, were about also $500-600, so a little bit more expensive, because I had a very difficult ignition system with spark, not with spark plugs, with a hot platinum wire and a little hydrogen flame, which was supposed then to ignite in turn the mass of fuel.
Can you tell me how much the model cost to make?
The total cost, I would estimate very closely to 1,300 marks. That, to give you a feel, would buy you a little car like my Opel was, a good sports car comparable to a Porsche would at that time cost in the neighborhood of 5,000–6,000 mark.
How did you manage to afford the money?
I saved a little bit, as a matter of fact, and sold even some of my optical equipment, like a Leica and like other optical equipments which my grandmother had given me. And the rest I asked my dad to help, and also I had a little bit money saved from my allowances.
What happened when you first joined Heinkel?
When I first joined Heinkel, I wanted to build combustors, because the combustor was the point which gave us the greatest problem. But Heinkel was so very impatient and wanted to fly. I felt I had that strange sense of insecurity, and I couldn't expect any help from the rest of the people at Heinkel because we didn't know each other. I was new and very young. And when I walked on the Baltic Sea beaches during the nights to think about what to do, I came to the idea, why not build a demonstrator strictly with hydrogen, because I felt my system of a radial outflow compressor with a radial inflow turbine was completely secure and absolutely sure to work. And now when I would have an equally sure combustor with hydrogen, which I think I could build, then I thought I have an engine which demonstrates the principle so beautiful and so impressive that no one would even think to fire me anymore, and I would get the support for getting more.
Can you remember when the hydrogen demonstrator ran?
When it ran was about 1937. And our designer was a man Gundermann, who liked always jokes and limericks and this kind of thing. And he said, hey, we built it in 9 months, meaning that it takes a baby 9 months, and it took us with a gas turbine 9 months. Also, I remember when we ran the engine, it was extremely impressive when the puddles of water, the water was blown out and gave a fantastic picture. Now, sometime when Heinkel brought people in and we had night frost, then the mechanic went quickly around and with his feet destroyed the ice so that the ice blocks and the water flew. Now these are very strange ways to say when was that. Now the fact is exactly, I cannot give it to you. I wasn't interested in the history or so. I didn't see myself at that time as a museum piece or any such thing. I was just thinking what we do now and next. And I felt that was the obligation of Heinkel's people to do that. Now we all remembered that it was around that time, but Heinkel in his memoirs wrote 17th of September 36, and I did a terrible thing. I overlooked that in when he gave me the proofreads, or rather an initial to read, and so I was very happy when I saw that, and don't know how it came, probably because we had another engine at that time which fits about that date.
Fine, thanks very much indeed. The thing I was going to mention here, of course, was that it's just about the same time as Whittle's first engine ran, although you weren't aware of his work.
Now, I always object to comparison because Whittle's engine was, in a sense, much further advanced because he did not do it out of psychological reasons and utilizing gaseous hydrogen. He already had lost a lot of time with the first fuel combustors. Whittle's work he started to design it in mid-35.
Well, you went from the hydrogen engine to what?
To the gasoline engine, which really would be an airplane engine, driving an airplane.
Presumably your stock, your esteem in the company went up.
Oh yes, it was very nice. I became division chief. I was reporting directly to Heinkel, and I became very much befriended with the Günthers, or with Siegfried Günther, because Walter had an accident, died. It was a very, very nice time, very hard work, because Heinkel was very impatient. He wanted to fly very soon. So that was a wonderful time.
What sort of a day did you have then? I mean, you said you worked very hard.
Well, it was not from any time, you know, it was till night till, and at home you still worked, and so you really wanted to succeed.
The Heinkel 178, who designed that plane?
The Günthers, Siegfried Günther made the, I think Walter Günther was the man who made the aerodynamic design, and it was then that he had that deadly accident and his brother continued. Now the engine, the flight engine, I would call it the first engine, not really the final engine. The first engine which was flying was the 3B, and it was an engine which had about the same rotor as we had tested, namely a radial outflow compressor and a radial inflow turbine. And the combustor was, upon suggestion of Max Hahn, he gave me a very nice suggestion to put it in front. So we had a reversed annular combustion chamber, and that made it possible that rotor of the compressor and rotor of the turbine were extremely close together.
Could you test the parts individually?
No, we had no test stands, but it was very fortunate when you have a radial inflow turbine with the same diameter about as the compressor, they are automatically matched. So it was a great advantage, and the temperature, the operational temperature, was determined by the cascades.
Were materials a problem to you?
For mass production, yes. But for the first engines, we used very good alloyed austenitic steels. Later on, we had to think, for the real production engines, we had to think how to cool the turbines with air. And the actual flow turbine was by far easier to cool than the radial flow turbine. But in the very beginning, we had enough headaches with the problems of performance and safety and endurance that these problems came a little bit later.
What were the characteristics of the Heinkel 178? It was never designed to be anything but a prototype, right?
Yes, it was designed to produce an aircraft system which showed the principle. Now, Heinkel probably was very much forced, like I was forced, to use psychology to have something first to show and then get ultimately the facilities for it. You know, his goal was to buy a airplane factory, and it was almost at that time an unbelievable, crazy hope to do that, but he did it.
Sorry, in what sense did he do it?
Oh, you see, after we had the very first flight, he invited the Air Ministry to come, and that was just when the war sort of broke out. The troops went over to Poland and England and France. As I recall, after the first flight, we learned through the loudspeaker that we were actually in war with England and France because they stood to the guarantee for Poland. And then Heinkel invited the higher level Air Ministry people. They were not really overly enthused about the flight performance demonstrated by the Heinkel 178. And Heinkel used, however, that opportunity to show to the Air Ministry his first prototype fighter design or concept, which was a two-engine outboard mounted type of a fighter. And he got the contract, and he made with Udet the strange arrangement I never could understand, that when he can hold the date that it flies in about April of 1942, then he would get the money and could buy the factory. Early in the morning, a small group from Heinkel's people, very selected, could witness when Warsitz took the machine off into the air. And I remember distinctly our fears and our wishes. And it was, I don't know exactly, 4 o'clock or something in the morning, and a light fog, very little, just I would call it light dust, when he started, and then he disappeared. And after a while he came back, and we thought, oh, he's landing. He didn't. He made another round, and we said, oh my God, he must like it. But we didn't have the airplane very filled up with gasoline, so we hoped he would come back, and pretty soon he actually came back, slipped, made a slight slip, and landed. It looked like very skilled and absolutely simple, not anything difficult, and he landed and stopped the airplane just where Heinkel stood, and the whole group of Heinkel. So that was very, very good and well done. But we found out later on that it wasn't that he enjoyed the flying, but he couldn't see the glare of the dust on the ground when he came from the higher level. He couldn't see early enough the field, and so he couldn't land, and made a shorter curve and then landed. So that was but it was still a wonderful story, and he said everything functioned beautiful, and the engine worked well, and he was really himself very enthused. We had a nice festival.
And then Heinkel went off to phone Udet.
He called Udet. I didn't know. He didn't tell me I will now call Udet. I learned later on he called Udet and he said, "Hey, congratulations, but let me sleep. That's an ungodly time." And
so the advent of the jet age.
yeah, that was an ungodly time. And he probably was called by 7 o'clock or 6 o'clock in the morning.
Up to that time, you had presumably had really all the resources you needed. You weren't in the case of Frank Whittle, who was trying to grasp every penny he could get.
No, we didn't have money problems, although we were, by nature, this project was extremely inexpensive by its very nature. We didn't need much tool machines because we used his few lasers, the bigger ones, which we didn't have. We went to the shipyard, which was at Jetzen, and paid a little bit for that, was not expensive. So actually, the whole development was very inexpensive, but when we would have asked for more money, we would have gotten it. So money was not a problem. Designers was a problem. We didn't have engineers. We had one good designer, Mr. Gunderman, who was really very nice to work with, and a few draftsmen, and no machines and no test stands. We could not make any compressor or turbine testing.
What was the attitude of the Air Ministry towards Heinkel and the engine?
Well, first they didn't know much about it, if any. And once they learned in about early summer 1938, that was more than a year before we flew, the Air Ministry was very positive to the idea of jet propulsion, and Hans Maug said, very thankful to Heinkel and to me, that he didn't even know anything about the concept of jet propulsion. But in a very short time, he studied it himself and came to the conclusion that it's a key to future fighter aircraft. So he was absolutely more than positive. He was enthusiastic for jet propulsion for airplanes.
But over him? Over
him was Eisenlohr, and I do not know when he started to explain it to Eisenlohr. Maug was a man who felt so strong for himself that he didn't care much, I believe, what his boss said. In addition, he was a very good friend of Udet, because both were pilots. Maug was a pilot too some time ago. And so I think Hans Maug was not so much in any problem or had a problem with the higher echelons of the Air Ministry, but he had the following problem. He couldn't persuade Heinkel to give the production up and send me and the group of engineers to Daimler-Benz what he wanted. And Heinkel just simply said no to it. And Helmut Schelp, who was much more trained in the area of jet propulsion, he did not need to be persuaded. He was already very much convinced, and he joined Maug as his right-hand man, and later on became his successor. Now, Helmut Schelp felt, yes, we, like Maug, we have to get the big industry into it, but we don't have to push Heinkel out. In contrast, he thought that Heinkel's work made it easier for him to have a backing against his higher echelons, because there was already an airplane flying now, pretty soon, I mean. And he wanted that Heinkel produces as much as possible evidence and also to persuade the industry.
The circumstances of the first flight, were you apprehensive or were you certain?
Oh no, I was very certain that it would work. But of course you always feel there's a danger, and we had made not too many pre-tests. We ran the engine before it flew perhaps several hours at the very most. We had one rotor which we ran 10 hours, but we didn't fly with that because we investigated what happened. Nothing exploded, nothing went wrong after the 10 hours. But we had really, we thought each time it's good when it's over. You know, that kind of bearing go, nothing will explode. We knew in the engine, even when you have a failure, you can still land. That we were absolutely sure. But we were afraid that something could happen to the bearings or to the blades.
Can you tell me now about the German Air Ministry demonstration in November?
Heinkel invited the Air Ministry to come, and I do believe that the highest who came was Udet, and I know a man with the name Reidenbach, which was very high up, but I don't know exactly how high he was. And several others came, and Heinkel was first very disappointed. The people did not show too much interest, and Udet made many comments that Warsitz should come and land. One cannot fly so long with such an airplane. And Heinkel was very unhappy. And then came that big breakfast they had, and somehow Heinkel used that possibility to offer a new design of a two-engine fighter aircraft. And actually, he got the contract about 2 months later. It was accepted by the Air Ministry, and Udet and Heinkel made an extra kind of deal. I don't know why and what the meaning was, but it was this: when Heinkel can show the 280, which was that new airplane, fighter airplane, could fly by about April 1941. Then he would be able, or would get the permission to buy the Hirt Corporation.
Which would give him all the skilled engineers that he needed.
Oh yes, Hirt had the most fantastic group of engineers, testants, component testants, and that together with our engineers would have been a fantastic team.
Tell me, what did you go on to do after the first flight of the prototype? Did you go on to work on other engines?
Oh yes. There was that point in 14 months we had to fly with a 280. Heinkel had two projects. He had the project of Herbert Wagner, which was a small diameter axial flow gas turbine, and that would have been a beautiful propulsion system for the 280. However, the group of Herbert Wagner, which now worked for Heinkel, was very much in doubt whether they could make it in that short time. And so Heinkel pressed me very hard. What can we do? We have to have this flying in order to buy the Hirt Corporation, and all our problems are over. And I had now a tremendous risky thing, namely, I had to use the rotor type of our first flying aircraft, but we had to make the diameter very small, and I choose for that an actual kind of diffuser, which was unbelievably risky. I asked the DVL, Deutsche Versuchsanstalt für Luftfahrt, and they said that won't work. An axial flow compressor is not suited for an axial flow diffuser is not suited for a radial flow compressor. So I get very discouraging views. Now, we built nevertheless one, and a through-flow annular combustor, which was the most compressed type of combustion facility. Now, with that, we tried to make it, and I had so little time, and imagine in 14 months we had really gotten the performance almost, but ready to test on Heinkel's small airfield, and it worked better than we thought. So actually it was a gamble, and we were lucky. It was not a real honest development.
You've, just an aside, but when we last saw you in Florida, not here, you said that you have been generally lucky, haven't you? You were telling me that you believed that at certain times you had a guardian angel.
Yes, particularly in my decisions to whom to go and what to do and how to do it. There was definitely an unbelievable amount or accumulation of good luck. And after I heard our great Newman, Gerhard Newman, who has the philosophy, luck is everything, so I had quite a bit of it.
Just going back for a moment to the demonstration in November 1939, would you regard that as a turning point in the German Air Ministry's attitude towards jet engines?
Yes. Udet came to Heinkel and almost embraced him and said, it is unbelievable. He was so enthusiastic after he saw the 280 flying. It was really a tremendous impression. It was for them now a well understood vision of the future.
You said 280. Did you mean the 178?
No, not the 178.
It's the demonstration of the 280?
Yes.
When was that, Hans?
On that day where Heinkel got the factory, the permission to buy the factory, namely in 41.
I'm talking about November 1939, though. The demonstration.
Oh, that was not the turning point.
Not the turning point. No. What was, do you think?
It was no one dared to touch Heinkel, so it was a step. But the real turning point was the flying of the 280, where he got now the permission, which is unbelievable, unheard, in the middle of the war, that Heinkel became what he always dreamed, a turbine manufacturer, because he had everything now, manufacturing facilities, engineers. After the flight with the 178, he only had gained a position that they could not brutally squash him out. They were not very enthusiastic. Udet was not overly enthusiastic. He was more concerned about the life of Warsitz, and that looked a little bit, particularly when I tell you the sad part of it, that they couldn't get the landing gear in, and so they flew with the landing gear out. And that looked anyway not extremely elegant when Warsitz came and went down to the spectators. They said, oh my God, this doesn't look good to us. And no, the flight of the 178 only opened the door for him to get the contract for the 280. And that was really the turning point.
Excellent. I mean, that's clearer than I've ever heard it before. Thanks very much. But it was the case, was it not? And perhaps you'd give this back to me. It was the case, was it not, that the lower echelons of the Air Ministry were really quite enthusiastic?
Well, they were very happy because they knew now that their plan with the engine industry, no matter what, could not endanger them anymore, because after all, Heinkel flew. And they pressed and could really allocate large resources to Junkers and BMW. in that sense, yes, it was an additional turning point. It gave all the backing for the lower echelons of the Air Ministry that they made these contacts with BMW and with Junkers.
Can you tell me something about the engine you were working on during the war, the 011?
Yes. The Heinkel 011 was actually a combination of the Wagner symmetrical compressor with a diagonal inducer stage, which we had sort of invented to shorten the whole thing and make it possible to go to very high pressure ratios without variable geometry. This was one of the most difficult problems, to get to high pressure ratios up to about 8:1 and have constant fixed geometry. That compressor could do it. And then Helmut Schelp helped very much in getting a two-stage turbine into this arrangement of the high pressure ratio compressor. And so we had an engine which was not only extremely high in thrust per frontal area and per weight, but also a very simple engine for very high pressure ratios, which was essentially considered impossible.
Essentially a revolutionary engine.
Yes. Yes.
Can you, looking back...
I said, unfortunately, yes.
Don't worry. Looking back, did you ever foresee the jet engine doing for travel what it has done?
Well, I think I began to see it, that it has unbelievable potentialities, even in supersonics. In the time period in the 1960s, I began to see that there are enormous possibilities. But I didn't see the possibility of long range in the beginning of the jet development. But the supersonic and long range I began to see in the 60s and get more and more. This was a gradual process to see the potentialities of it up to high Mach numbers.
Really, you, the inventor, didn't foresee mass air travel as that?
No, I've thought in the beginning it would be more for special aircraft of very high speed, but I didn't see it because it had so much fuel consumption. I didn't see the potentialities of reducing the fuel consumption so much that it would be also better than having a diesel aircraft. Efficiency, the overall efficiency of, for example, a Mach number 2 aircraft with jet propulsion is by far better than the best diesel engine. And therefore the range possibilities are dramatic. The reason why the ranges, or why the Concorde or the current supersonic aircraft are still not as economical as the transonic aircraft is not the engine. The engine is way better than in lower speed. But it is the drag-lift ratio of the airplane. The airplanes the supersonic aircraft have about a lift-to-drag ratio like the early Wright brothers had. And so the work has to be done on getting better and better lightweight and high lift-drag ratio aircraft, supersonic aircraft.
Where do you think the engine as a whole, where do you think that its future is? I tell you what I mean by that. It's a vague question. What I mean by that is that it's frequently said that in fact there will be fewer and fewer designs for new jet engines, but
Yes.
there will be a great deal of weight saving and more economies of scale and so on. Is that the case?
Yes, I think that is right what you are saying, but the amount of improvement is still a question of how much you trust in the evolutionary improvements of these engines. And I, for one, believe that we can get the efficiency still greatly improved, and the weight of the engine unbelievable, drastically reduced by a factor 2, perhaps even 3. And that has a tremendous snowballing effect on everything, economy and range and price of the engine, weight of the engine. So there are evolutionary trends which in the next 50 years will do something which looks like a technological breakthrough in comparison to the engines today.
How are we going to get that weight saving?
Oh, the weight saving is a combination of, unfortunately, a combination of a large number of things. Materials, for one, is a great one. The so-called structural materials, which are fibers and carbon and this kind of materials. Another thing is that the number of stages will be greatly reduced of the compressor, and therefore the length and the diameter will be further reduced, and this together with the materials can make a tremendous effect.
Is the prop fan the way to the future?
As long as you think of speeds in the 500, 550 miles per hour, there is a possibility. Of course, I have found there are 3 possibilities. One is the prop fan, which is questionable, however, from a standpoint of noise and vibrations, but it is certainly a possibility. The other is that you may utilize large shrouds and use these shrouds also for stabilizing the airplane so that you have multifunctional effects. And thirdly, it is a very funny thing, and that is when we have aircraft which will have up to about 600 or 700 miles per hour, the same lift-drag ratio, we had that famous man in NASA, Whitcomb, when we can get such type of aircraft, then you need much less bypass ratio, and then you can fly very economically with near sonic speed, and you don't need the propeller, the prop fan, I should say. So what actually, in what direction the future goes is hard to say, but the prop fan is certainly a candidate.
Do you foresee a large economic supersonic transport, supersonic airliner?
Yes, I do. I believe that the supersonic transport will become reality due to a combination of excellent improvements. So one is definitely that the lift-drag ratio of future supersonic aircraft will become a possibility. Furthermore, that the materials have a much stronger, the improved materials will have a much stronger impact on the supersonic aircraft than on the transonic aircraft. And saving weight and better structures will also have a tremendous impact on the economy of the supersonic aircraft. So a combination of various things. I do not believe that the efficiency of the supersonic engine will much improve over the current one, but the other components will, together with the engine, make it possible that it's economically feasible.
You have had a very long career in jet engines. Are you, as an inventor, proud to have been the first to fly? Does it give you great satisfaction looking back?
I never really felt that way at all. No matter what I did, I thought when it did the success which I wanted to have, that was good enough for me. What you call success in the way you asked me is more than that, and I had never much interest in that.
What, you'd never much interest in worldly success, do you mean? Or
Yes, no. I just said that I could do what I wanted and that it succeeded somehow. Yes, that did give me satisfaction.
Mm-hmm. Finally, once and for all, as a student, could you have foreseen any part of the last 50 years in aviation? It seems to me to be unbelievable.
No, it was difficult to foresee that, and it is very difficult to say at what point. You know, it all depends on what point you saw what. And at the time I was a student, I sure did not foresee these things. But later on, I foresaw a little bit, and later on, even more, and so on. So right now, I am pretty sure that I can foresee clearly the air-breathing potentialities in form of vertical, in form of slow takeoff and landing, in form of long range, in form of economy, in form of speed. And speed is one of the greatest frontiers, because you want to go faster than 500-600 miles when you go from here to the other end of the world. And I do believe that the combination of the ramjet with a current turbojet will be the key to this future, and the air-breathing ramjet will also be the key to more economical communication with outer space satellites.
The P-51 Mustang, the most dominant escort fighter of World War II. It helped blaze a trail from England all the way to Berlin for America's bomber force.
Of course, the Mustang was a revelation. It was the war winner.
Its creation was sparked by a mixture of genius and chance. The Mustang and its two-stage, two-speed supercharged Merlin engine were the end result of years of technological development. From World War I to World War II, each generation of aircraft went ever higher and faster. But the Mustang's marriage with the Merlin might never have happened. National pride delayed the coupling of these two great innovations. But a new deadly German adversary changed everything.
The Focke-Wulf 190, this was really a top-notch fighter aircraft.
With the FW-190 terrorizing the skies of Europe, the British and American forces swallowed their pride and joined together to create the ultimate fighting machine. December 17, 1903. The Wright brothers' aircraft, the Wright 1, successfully takes off, initiating the dawn of aviation. Man had already taken to the skies with gliders and balloons, but this was the first time that an engine had propelled him into the air. The Wright 1's engine was a crude design by today's standards and put out 12 horsepower only. It was an inline engine, meaning that its cylinders, 4 in total, were mounted in a straight line. a layout that would inspire some of the most advanced piston-engined aircraft ever created. Though a simple design, the Wright engine was innovative. It was the first engine to make use of a lightweight cast aluminum crankcase. Every pound counted. With a heavier engine, the Wrights may not have made history that winter's day in North Carolina. Aircraft weight and power would continue to be important to the evolution of flight. World War I was approaching, and the newly formed air forces of the world needed reliable engines with enough power to sustain flight during operations. From France would come a new type of power plant to take the fight into the air, the rotary engine. Rotary engines operated differently than the inline ones used by the Wright brothers. The cylinders were arranged in a radial pattern rather than a line. When the engine was fired up, the crankshaft remained stationary, while the crankcase and cylinders rotated around it. A rotary engine had one giant advantage over the inlines of the era. It was much lighter, and thus gave a pilot better performance during combat or while trying to evade an enemy. However, the rotary engine was not without its shortcomings. It had poor fuel economy, as it was often run on full throttle. It also provided an unpleasant ride. Castor oil was mixed with the fuel mixture for lubrication, with the side effect of heavy fumes, smoke, and an oil shower for pilots. Turns with a rotary-powered aircraft could prove treacherous. As the whole engine rotated, it produced a gyroscopic effect. A turn to the right, at full power and low level, could end with the death of a pilot. Rotary-powered aircraft remained part of Air Force inventories till war's end, but they were gradually supplanted by the inline engine. Inlines based on the same principles as the one found in the original Wright plane kept improving in terms of power and performance. Between the wars and across the Atlantic, a new type of aircraft engine would emerge to dominate American aviation. The U.S. Navy was looking for aircraft to populate its fledgling aircraft carriers. Space on board was extremely limited, but aircraft with inline engines often had lengthy noses. Their engines, built with rows of cylinders, took up too much space on cramped carriers. Rotary engines, though more compact, had too many other weaknesses to be serious contenders for the role. There was, however, a third type of engine. Before the war, there had been limited experimentation with radial engines. At first glance, these appeared to be just like rotary engines. It's only when they are fired up that the difference becomes clear. In a rotary engine, the crankcase and cylinders rotate around the crankshaft. But with a radial engine, the crankshaft rotates while the engine block is static. Radials often weren't as powerful as inline engines, but they were less complicated. They were cooled by air rushing over the engine rather than through a liquid cooling system. This made radials less vulnerable to battle damage, which might rupture the coolant lines. Navy pilots who might have to travel long distances over the ocean to get to a target needed an engine that would be sure to get them home under any circumstance. Most importantly for the Navy, radials were smaller than inline engines, so a greater number of aircraft equipped with them could be stored on board their carriers. The Wright Aeronautical Corporation, a successor to the original Wright Brothers Company, used their aviation expertise to create the first reliable radial engine for the Navy, the J-5 Whirlwind. The J-5 was put on display for the entire world to see when Charles Lindbergh crossed the Atlantic in his Spirit of St. Louis in 1927. His flight solidified the reputation of the J-5 Radial as a dependable power plant. The budding airlines of the world were looking for engines to power their airliners and to bring their passengers across continents and eventually across the globe safely. reliable radial engines seemed to be the ideal choice. Radials would power many of the principal airliners in the history of civil aviation, from the Ford Trimotor to the Boeing 247 to the Lockheed Model 10 Electra. Both the U.S. Navy and U.S. Army Air Corps would rely heavily on radial engines as they built up their inventories of fighters and other aircraft. In the 1930s, the U.S. had just one inline engine in development, the Allison V-1710, an engine that would one day power some of America's great fighters. At the time, relying on radials seemed a prudent decision, but in the years to come, and in the battles ahead, it will leave the U.S. playing catch-up with their allies and enemies in Europe. In Europe in the 1930s, air forces and aircraft manufacturers were looking for speed above all else as they designed the next generation of fighters. Using streamlined designs and powerful V-12 inline engines, they put